Students, can you all hear me? Can you all hear me? Right, okay. So I think all of you can hear me now, and you can see the whiteboard also. So we have complete first. Uh, so I thought to revise all the theories again, as I mentioned you, a speed revision, kind of a revision from the beginning, unit 1 atomic structure. Okay. So I'm going to discuss the most important theory parts, right? So from the beginning, that is very important for the examination under this session, in this session. So let's quickly revise these things and let's figure out and what are the things we have to revise here, right? Okay. Right. Unit 1, atomic structure. So let me start from the introduction and the atomic theory. So I'm going to choose some topics. So under those topics, we can quickly revise everything, right? Introduction and the atomic theory. Right. So can you remember under the introduction and atomic theory, we learn about atom. What does mean by atom, right? So the ancient definition for the atom. So first of all, we have to revise that atom. The word atom is came from actually a Greek term, atomos, right? Atomos. Atomos means actually we know that this is indivisible. Indivisible. We consider those particles are uncuttable, right? Indivisible or uncuttable particles. So that's the mean of the atomos. So later this atomos term came for the atom. So in ancient time, they were thinking that the matter is made by atom. We know that everything in this world can be divided into two parts, two main parts, matter and the energy. The fundamental particle of the matter they considered as the atom. So the atom term came from the atomos, right? Atomos means indivisible, uncuttable particles. As the first atomic theory, the first atomic theory, as a theory, who represented the first atomic theory? The first person is actually John Dalton, right? John Dalton. So we discuss about the atomic theory, John Dalton's atomic theory. So the main concept of the John Dalton's atomic theory was, right? John Dalton's atomic theory main concept was what was the main concept? Main concept was actually he represented a model for the atom, atomic model, John Dalton's atomic model. We are going to revise the atomic models also from the beginning. So John Dalton's atomic model is, so John Dalton assumed that atom is look like gold, right? Gold, remember, gold. So the goal of the atom presented by John Dalton. So gold is atom is uncut. That is the particle, the ultimate particle we can find in matter. So that was the John Dalton's atomic theory, right? So under the introduction atomic theory, we discussed mainly about these things. I told you that Michael Faraday. So this one very carefully. These are very important. Michael Faraday and some bunch of the scientists, they conducted some experiments on the electricity, right? they conducted some experiments on the electricity. So they tried to send the current electricity. They tried to pass the current electricity through the solid medium, and they successfully conducted those experiments, and they have proven that through the current, through the solid medium or liquid medium, current electricity can pass, right? And some of the scientists actually tried to pass the current electricity through the gas medium, right? So what accidentally they found some of the negatively charged particles when they are conducting this experiment. That experiment is known as what? Cathode ray experiment, right? So the main topic, right? The first main topic that we discuss under the atomic structure is cathode ray experiment, right? I believe you can remember these things. If you can't remember these things, quickly revise these things. Cathode ray experiment, right? Can you remember who are the scientists actually conducted the cathode ray experiment? Who are the scientists? The first name is actually J.J. Thomson. J.J. Thomson, right? Let's quickly revise the names. J.J. Thomson. And then Julius Plucker. Julius Plucker. Then Wilhelm Hittorf. Wilhelm Hittorf. Write the names carefully, right? Wilhelm Hittorf. And then the important name, one of the important name here, what? Sir William Crookes. Sir William Crookes. Sir William Crookes. Remember, these bunch of scientists actually, these scientists conducted the cathode ray experiment in order to check whether current electricity pass through the gaseous medium. So that was the experiment, right? I told you that when we are discussing about the story of the electron, remember, they found the electron accidentally, right? Actually, their intention was to find out whether the current electricity passed through the gaseous medium, right? Who are the scientists conducted this experiment? J.J. Thomson, Julius Plucker, Wilhelm Hittorf, and Sir William Crookes. These are the people actually contributed for this experiment. So this experiment known as cathode ray experiment, right? So their intention was again to check whether the current electricity passed through the gaseous medium. Remember, sometimes you will be tested in the MCQ paper. Sometimes you will be tested regarding these things. Very careful, huh? Be very, very careful. So what was the cathode ray experiment? You should be able to describe what does mean by the cathode ray experiment. So I'm going to draw the cathode ray tube. Can you remember the cathode ray tube that we drew? Let's revive the cathode ray tube quickly. In this way, we can have a tube, right? Heavy, very strong glass tube. So this is a glass tube, right? Inside this glass tube, there are two metal plates. So these are two metal plates. Remember, these are two metal plates. This is a negatively charged metal plate, right? Since it is negatively charged metal plate, this is known as cathode, right? And this is known as anode, since it is positively charged one. Cathode and the anode. Cathode is negatively charged, anode is positively charged, right? Cathode and anode. Negatively charged one is cathode, positively charged one is anode. And then they have connected this cathode ray tube, that means two metal plates, to a high voltage source. They have connected this one to a high voltage source, right? So that is about 10 kilovolts, right? So this is high voltage source. High voltage source. If it is connected to high voltage source, they observe that from the cathode side to anode side, some radiations are emitting, right? Some of the radiations are emitting. Remember, if we keep if we keep a fluorescent screen, remember fluorescent screen means actually a screen that is sensible for the radiations, right? So if the radiations are passing through some medium, if you keep the fluorescent screen, we can see the radiations, right? That means some kind of rays are emitting, right? So I showed you that at the beginning, I showed you that cathode ray experiment, some of the green color lights are emitting. Remember, cathode rays are not green color. Remember, cathode rays are not green color. Because of that fluorescent screen, we can see the cathode rays in green color, right? So therefore, don't misunderstand. From cathode side to anode side, they observed some radiation through the fluorescent screen. We could see that one in green color, right? Listen to what I say here. What did I say you? They observed that from cathode to anode, some of the radiations are emitting. In the presence of a fluorescent screen, they observe these radiations in green color. So these are known as cathode rays. Remember, these are known as cathode rays. Why they have given a name like cathode rays? The reason is these cathode rays are emitting from the cathode, right? We are going to learn about the anode rays also, but anode rays are actually positive rays, right? Positive rays are not actually, we are not giving the name anode rays. Commonly, the name that we are giving is positive rays, right? So positive rays are not emitting from the anode, but cathode rays are starting from the cathode. If you analyze the past papers, actually, they have given some of the questions regarding these things also, right? Cathode rays are emitting from the cathode, right? And now, so this was an accident, I told you, right? This was an accident. They observed green color, they observed some radiations emitting from the cathode towards the anode side. And J.J. Thomson, right? Sometimes this tube is known as Crookes tube, in order to honor that Sir William Crookes. So he's the founder of the tube actually. So therefore, sometimes this is known as cathode ray tube. If not, we consider this one as Crookes tube, right? And I want to remind you that the pressure inside the glass tube was 1/100 mercury millimeter pressure. So that was a very low pressure. Okay, that was a very low pressure that they have maintained, right? And they have supplied high voltage source. Since they are supplying high voltage source, remember inside the glass tube the energy is very high. So therefore they have reduced the pressure also. So they have maintained some conditions. Anyhow, they observe some radiations emitting from the cathode, and they are moving towards the anode. These are known as cathode rays, right? So, so now only J.J. Thomson, the scientist J.J. Thomson is coming to the play. Actually, he observed this one. Actually, he re-observed these radiations, and he conducted several experiments on the cathode rays, right? Can you remember what are the experiments conducted by J.J. Thomson on the cathode rays? Can you remember them? So let's discuss quickly one by one. What are the experiments conducted by J.J. Thomson under the cathode rays, right? On cathode rays. So they were shocked, right? They didn't expect this kind of radiations in this experiment. So therefore, J.J. Thomson re-observed these cathode rays, right? So when he observing these cathode rays, I'll take the summary of the experiments. Experiment carried out by J.J. Thomson, right? And then let's go for the observation. Sorry, yes, observation. And then let's go for the conclusion, right? Conclusion. I'm not going to discuss the diagrams here, because rather than drawing the diagrams, we can summarize what is the concept about that experiments, right? So actually there were three main experiments. Can you remember what was the main experiment conducted by J.J. Thomson on cathode rays? The main experiment was J.J. Thomson kept an electric field, right? He kept an electric field in the path of the cathode rays, right? We know that in the cathode ray tube, right? In this way, cathode rays are emitting in this way, right? So he kept two metal plates. This one is positively charged and this is negatively charged. These cathode rays are deflected towards the positivity. So this was the experiment that we discussed. Okay? So the cathode rays are actually moving towards the positively charged plate. That means if they created the electric field, if they have created an electric field, these cathode rays are moving towards the positive tip of the electric field. If the cathode rays are moving towards the positive tip of the electric field, means definitely we can observe, we can conclude that cathode rays are negatively charged. So that was the main conclusion. So therefore, let's write down the experiment. What was the experiment? He created an electric field. Let's write down this one. Kept an electric field. Rather than writing kept, we can write down created an electric field in the path of cathode rays. And what was the observation? Observation was cathode rays deflected or deviated towards the positive tip of the electric field. Positive tip of the electric field. Then we can understand what is the conclusion. Conclusion is cathode rays are negatively charged. So this was the main experiment conducted by J.J. Thomson, right? He didn't know what are these radiations, right? So therefore, he reobserved these radiations and he conducted several experiments to identify the properties of these cathode rays. So this is the first one. Finally, he concluded from his first experiment, these cathode rays are negatively charged. If you go for the second one, can you remember in the second one, we drew a diagram like this. In this way, we have the cathode ray tube, right? In this way, we have the cathode ray tube, and here we have cathode, and here we have anode. This is the cathode. So J.J. Thomson, he kept a metal cross kind of object, right? We can see that simply that is an object, right? Metal cross. When he kept the metal cross in front of the cathode, he observed that image of this metal cross. Here, he reobserved the image of the metal cross in this way. So this is the image, mirror image of the metal cross. So therefore, he concluded that cathode rays are travel in a straight line, right? You can see the exact image, right? You can see the exact image of this metal cross of the opposite side of the glass pole. That means cathode rays are travel in a straight line, and cathode rays have properties like light, right? They are travel in a straight line and they have the properties like light. So therefore, he concluded that cathode rays are travel in a straight line. So what is the experiment? Experiment was kept a metal cross, an object, okay, in front of the cathode. Then he observed, what did he observe? He observed that mirror of the cathode, that means image of metal cross at the opposite side of the glass wall, right? So we can see that, right? So you can see that the conclusion was cathode rays travel in a straight line. Cathode rays travel in a straight line. Like light, right? So from this one also we can conclude that actually, so this is another conclusion, cathode rays have what? Wave nature, eh? Cathode rays have wave nature, because we know that light has wave nature. Number 3, what was the third main experiment? Can you remember the paddle wheel? So in front of the cathode, he created a wheel, so small wheel. We consider that one as a paddle wheel, right? Some kind of a wheel like this, right? in this way, and cathode rays are colliding with this paddle wheel, and this is started to rotate, right? So this is cathode and this is anode. So this is started to rotate towards the anode, right? Cathode rays are colliding with the paddle wheel, and this paddle wheel started to rotate towards the anode, right? So that was the observation and the experiment. What was the conclusion? Conclusion was what? Thomson decided that cathode rays have particle nature, right? They can do a work. Particulate, yes, particulate. Cathode rays are particulate, they can do a work. So that's what J.J. Thomson concluded, right? So therefore, third experiment was kept a paddle wheel in front of the cathode, and what was the observation? What is the observation? Observation is paddle wheel started to rotate, right? Paddle wheel started to rotate towards the anode, right? The anode. Then what was the conclusion? Conclusion was cathode rays are particulate. Cathode rays are particulate. So from this one, actually, we can imply something very important using this one. What is that one? So can we say that? What is that doubt? Can we say they have a force then? Yes, right? That means they can do a work, right? They have an energy, kinetic energy. We can apply the kinetic energy equation, half mv squared. We can say that these particles have momentum, because particulate means they have a mass, right? So therefore, here we can see the duality nature of the electrons. Later we are going to discuss about the duality nature. De Broglie's equation. Can you remember the De Broglie's equation? We are going to discuss this one. Okay, right? So these are the three experiments, three main experiments conducted on cathode rays by J.J. Thomson, right? So addition to this one, actually we can consider that cathode rays can ionize the gases, right? Cathode rays can penetrate through a metal plate. Likewise, there are some properties. Yes, Sinetma, correct, very good, right? So likewise, we can discuss some properties of the cathode rays, right? So finally, they got a conclusion. What is their conclusion? Cathode rays are none other than electrons. Finally, they found the charge of the cathode rays, right? Finally, they found the charge of the cathode rays. Let's see. Look at this one. Right? For the cathode rays, we are giving another name. So that is actually beta radiations. Right? Cathode rays are nothing else. What? Beta radiations. We consider them as beta radiations. Right? Okay. And then we have to discuss the charge and the mass of the cathode rays. Charge and mass. Remember, J.J. Thomson calculated the E over M ratio. Can you remember the E over M ratio value? Can you remember the E over M ratio value? No need. You don't have to write down these things. Okay, this is kind of revision I told you. So just listen, and if you have any doubts, let me know. Just listen, right? Take your notes and revise everything. So this is kind of a revision. You don't have to write down. Okay, in the theory class we have already written these things. Okay? So therefore no need. So remember, E over M ratio value is 1.759 10 to the power 11 coulombs per kilogram. So this is the E over M ratio for cathode rays. Who found this E over M ratio value? Who found this one? J.J. Thomson found the E over M ratio value. Remember, students, there was another scientist actually known as Robert Millikan. Right? Robert Millikan. He conducted an experiment. That experiment was known as oil drop experiment. Using the oil drop experiment, he found that charge of cathode ray particles are right? So there was a scientist known as Robert Millikan. What is the name? Robert Millikan. Robert Millikan conducted an experiment. That experiment was known as oil drop experiment. We don't have to talk about this in our syllabus, but you have to remember the name, oil drop experiment. Using the oil drop experiment, he calculated the charge. Remember, E means charge. E means charge, right? M, what does mean by M? M means mass, charge and mass, right? So he calculated the charge of cathode ray particles. Charge of cathode ray particles. He found that one as 1.602 10 to the power minus 19 coulomb. Coulomb is the unit that we are using to measure the charge of an electron, charge of any particle. Any charge particle, we are using the Coulomb unit. So the charge of the cathode ray particles was introduced as 1.602 10 to the power minus 19 Coulomb. Who found that one? Robert Millikan, using the oil drop experiment. Then later they found that actually from the other hand, Michael Faraday and those scientists, they found that the basic fundamental particle in electricity, right? Electrical energy is also what? That also electron. So here they found the charge of the cathode ray particle. That also 1.602 10 to the power minus 19 Coulomb. So later they concluded that cathode rays, right? Cathode rays are none other than what? Cathode rays are none other than electrons. So this is the symbolization of electron. Cathode rays are none other than electrons. So that was the conclusion, right? So look at this one. This summary is very important. Charge to mass ratio found by J.J. Thomson, 1.759 10 to the power 11 coulombs per kilogram. And the charge of an electron or the cathode ray particle found by Robert Millikan using the oil drop experiment, that is known as 1.602 10 to the power minus 19 coulomb. And cathode rays are known as, finally, electrons, nothing else, right? And cathode rays are known as beta radiations. How we can find out the mass of the cathode rays, right? How we can find out the mass of the cathode rays? Easy. If you know the E of M ratio value, remember, if you know the E of M ratio value, E of M ratio value, J.J. Thomson represented that one as 1.759 10 to the power 11 coulombs per kilogram. And the charge we know that 1.602 10 to the power minus 19 coulomb. So this is equation number 1 and this is equation number 2. From the equation number 1 and equation number 2, you can substitute the charge of an electron to the equation number 1 and you can find out the mass of an electron. What is the mass of an electron? Right? Can you remember what is the mass of an electron? 9.107 10 to the power minus 31 kilograms. If you say this one in grams, that will be 10 to the power minus 28. So this is the mass of an electron. Understood? So this is the mass of an electron. We know the charge of an electron. We know the mass of an electron. Mass of an electron is 9.107 10 to the power minus 31 kilograms. In theories, we did the calculations regarding this one. So go through the note and everything and recall these things, right? So now you can understand what are the main points you have to remember. Okay. So today I'm going to discuss all the main points as a summary of what you have to remember, what you have to revise mainly under the first unit. Okay. Right. So this is the mass of an electron. Right. And you should know that how to symbolize an electron. Very easy. Normally, the symbol of an electron is symbol of an electron can be written as in this way: E minus 1 0. Remember, students, this minus 1 is known as relative charge. Okay. This minus 1 is known as relative charge. And this 0 is known as relative mass. This is known as what? Relative mass. Why this relative mass and relative charge? Normally, when we are writing the symbol, this is the way we are writing the symbol. We can't include the absolute mass and the absolute charge. What is the absolute charge of the electron? 1.602 10 to the power minus 19 coulomb. What is the absolute mass? 9.107 10 to the power minus 31 kilogram. So we can't mention those things. So that is very complicated. If you write that one here, that is very complicated. So rather than telling the absolute mass and the absolute charge, better we can write down relative charge and the relative mass, right? So remember, when we consider the relative charge, normally what are the three subatomic particles we are discussing under the topic? Electrons, protons, and neutrons, right? So these are the three subatomic particles. If you consider these three subatomic particles, electrons are negatively charged, protons are positively charged, and the neutrons are neutral. So therefore, we have only two charged particles, electrons and protons. So therefore, we can give the -1 for the electrons, +1 for the protons, right? And if you consider relative mass, remember students, actually there is known as what? Something known as atomic mass unit. Atomic mass unit. So what does mean by this atomic mass unit? Right? Atomic mass unit. Sometimes this is known as one AMU, right? If not, we consider this one as 1 Dalton, right? The value for this one is 1.661 10 to the power minus 27 kilograms. So this is the atomic mass unit. Remember students, atomic mass unit is represented in order to take the masses of very tiny particles like atoms, molecules, electrons, protons, neutrons, because they have very small mass. Therefore, they have some value that is known as 1 or else 1U, 1A. This is equal to 1.661 10 to the power minus 27. Right? Can you understand? These values we can use in this. Now, why they have considered here? Can you all hear me properly now? Can you hear me? Breaking. Okay. If it is breaking again, tell me, okay? Let's see. Maybe some connection issues for me, right? Right. Now look at this one. Again. Okay, right. Now look at this one. Since I'm a little bit fast, sometimes you will feel like that, okay? Let's see. So atomic mass unit. So this is the atomic mass unit. Atomic mass unit is what? Represented in order to weigh the mass of particles in this way. Now, we know that the exact mass of the electron is 9.107 10 to the power minus 31 kilograms. So the exact mass is this one, absolute mass, and this is the atomic mass unit. Comparative to atomic mass unit, you can see that mass of an electron is negligible. Look at the mass of an electron is 9.107 10 to the power minus 31. So the mass of a atomic mass unit is represented as 1.661 10 to the power minus 27. So therefore, when you compare with the atomic mass unit, electron's mass is negligible. So that's why we consider the relative mass is 0. So likewise, we have a standard notation for the protons as well as neutrons, right? So this is the summary that we have to remember regarding the electrons, right? So we discussed about the cathode ray experiment, right? What are the experiments conducted by J.J. Thomson? And we know that what does mean by the E over M ratio value, who found that, and we know what does mean by the charge of an electron, the value 1.602 10 to the power minus 19 coulomb, who found that one, Robert Millikan, and the experiment was oil drop experiment. Later, they found that cathode rays are nothing else electrons. Mass of an electron is 9.107 10 to the power minus 31 kilograms. Symbol of an electron can be written in this way. So that is the summary. So always this summary should be in your mind. Remember students, atomic structure, the first unit is very lengthy unit, right? And you will realize that one, after 1 year, 2 years, these things will be nothing for you. Now you just finished the first unit and you are going to the second unit. You will think that in the first unit we have this much to remember, this much to memorize. No, it's not like that, right? you have to always keep a summary in your mind, right? So this revision will be helpful for you to what are the things actually we have to remember as a summary. We don't have to remember all the things, right? Before go for the examination, we should have a note, proper note, and we have to go through everything from the beginning. But we can't remember everything neither. Always we should have a summary in our mind. So that summary is very important, right? Okay. Now this is all about what? Electrons, neither. Now let's go for the next subatomic particle. What is the next subatomic particle? The next subatomic particle was proton. Remember, students, if you go for the protons, so the discovery of protons is also very interesting. So this is all about electron. Then let's go for the protons. So when we talk about the proton, actually we have to revise the name Eugen Goldstein, right? Eugen Goldstein. So this name is very important. Okay. This name is very important because Eugen Goldstein conducted experiment. He conducted experiment using again the cathode ray experiment, right? He again chose the cathode ray tube. He took the cathode ray tube and he observed in this way. Look at this one. I'll draw a diagram. Then you'll understand what was that. So I'm not going to write down the high voltage source and everything. So this is the diagram. So this is positively charged anode. And this is the negatively charged cathode. Cathode and the anode, right? So what did he do actually here? Negatively charged cathode and the positively charged anode. So he injected hydrogen gas here, right? He injected hydrogen gas here. So when he injected hydrogen gas here, hydrogen gas actually what? Colliding to the hydrogen atoms, because we know that from the cathode side, anyhow, from the cathode side, electrons are emitting. From the cathode side, electrons are emitting in this way. So these are the electrons. So these are the electrons emitting from the cathode side. Remember, students, now hydrogen molecules are injected to the cathode ray tube. These electrons are colliding with the hydrogen molecules, and this hydrogen-hydrogen bond is breaking. Right? Hydrogen-hydrogen bond is breaking, and furthermore, these hydrogen atoms are ionizing. These hydrogen atoms are ionizing by removing one electron. Okay? Hydrogen molecules are converting to the hydrogen atoms, and then they are converting to the hydrogen ions, cations. So these are H plus cations. Now in the cathode ray tube, we have H plus cation. Look at the experiment conducted by Eugen Goldstein. Now inside the cathode ray tube, H plus cations are there. So now in these H plus cations, what happened? This H plus cation started to move towards the cathode. Then Eugen Goldstein observed that some of the radiation, addition to the cathode rays, right? Addition to the cathode rays, some of the energy radiations are moving towards the cathode. So we can simply understand, right? We can simply understand if some of the particles are moving towards the cathode. Cathode is negatively charged. So therefore, definitely these particles should be positively charged. And they found the protons, right? We know that the simplest gas, the simplest element we can use is hydrogen. Simplest element is hydrogen. So this is the simplest positive ray particle. Actually, initially they gave a name, Eugen Goldstein gave a name positive rays, right? So we are giving another name, canal rays, right? So these are known as positive rays or canal rays, right? Positive rays or canal rays. These are known as positive rays or canal rays. So later, Ernest Rutherford gave the name as proton, right? So the most simplest positive ray particle is obtained when hydrogen gas is used. So that's why we consider that proton is nothing else. Remember, proton is nothing else, hydrogen nucleus. hydrogen nucleus, because we know that, students, if you consider the hydrogen atom, in hydrogen atom there is only one electron, and inside the atomic nucleus there is a proton. Remember, this is the one and only element without neutrons in the periodic table. This is the only element without neutron. So therefore we can consider this is actually, after removing this electron, we can consider this is just a proton. So therefore we can consider that proton is nothing else hydrogen nucleus. Neither. Therefore these are known as positive rays or canal rays. So this is the discovery of the positive rays. Actually, they how did they gave the approach for the positive rays? That means how did they thought? They think about this. Remember, atom is neutral. Atom is neutral. They found the negatively charged particle. If it is neutral, remember, negatively charged particle means negative charged particle is inside there. Definitely, then positively charged particle also should be there, right? If there is a negatively charged particle, definitely positively charged particle should be there. It's a must if it is a neutral one. Atom is a neutral one. That was the motivation for the Eugene Goldstein, to identify the positive ray particles, or else we can consider protons, right? So that's the story of proton. Then let's consider what is the charge and mass of the proton. What is that? If you consider the charge and the mass of a proton, so let's take a summary later about these three subatomic particles. Right. Charge and mass of a proton. Remember, students, if you consider the charge of a proton, this is also similar to the charge of an electron, 1.602 10 to the power minus 19 coulomb. Remember, okay? As a chemistry student, you should be able to remember these things. These things are nothing. And then if you consider the mass of a proton is equal to 1.672 10 to the power minus 27 kilograms. Right? So this is the charge of a proton. Yeah. If you have any doubts, put your doubts in the chat box, right? Right? Charge of a proton and mass of a proton. So charge of a proton is 1.602 10 to the power minus 19 coulomb. Charge of mass of a proton is 1.672 10 to the power minus 27 kilogram. And then remember, look at this one. What is the symbol of a proton? Symbol. How we can symbolize a proton? Proton is symbolizing in this way. P11. P11. Proton. We know that I told you that this is the relative charge and this is the relative mass. Relative charge. This is the relative charge and this is relative mass. Okay. So relative charge is 1, relative mass is 1. What do you think about it? We consider that in an electron, relative charge was, so this is the relative charge. This is relative charge and this is relative mass. I told you that when you consider the electrons, here we have written minus 1. Now here for the protons, we have to write down plus 1 because that is the charge of the proton, right? This is positive. Positive particles are considered as protons, negative particles are known as electrons. So therefore the relative mass is 1. We know that atomic mass unit 1 Dalton is equal to 1.661 10 to the power minus 27 kilograms. Students, compare these two values. 1.672, 1.661 10 to the power minus 27. Up to the first decimal point, two values are exactly same. Two values are exactly same up to the first decimal point. So therefore we can consider that the relative mass of a proton is 1, right? Mass of a proton, charge of a proton, and the symbol of a proton, right? Very easy. Very easy. And remember, we can consider that instead of this notation, we can use hydrogen plus 1 is also possible. And if you compare the mass of a proton and mass of an electron, remember the mass ratio, we discussed this one in the theories also, that is 1836. You can see that how tiny, right? How light the electron is. Okay, look at this one, mass of a proton and mass of an electron. Right. Okay. Now let's move for the story of a neutron. In the neutron, actually, we don't have discussed that much here. But anyway, let's discuss some important things regarding the neutron. Right. Neutron. Remember, students, actually, the discovery of the neutron is very interesting because if you consider the mass of an atom, the highest contribution for the mass of an atom is from the neutron, not from the electron or proton, right? So later, let's compare the masses of these subatomic particles, that you will realize which one has the highest mass. Actually, the highest mass belong to whom? Nothing else, neutron, right? So the highest mass always belong to the neutron. And remember, the neutron is actually inside the nucleus, right? Now, they thought that, right, when they found the mass of an atom, they found that there should be another subatomic particle inside the atom. Not only the subatomic particles, electrons and protons contributing for the mass, there should be another subatomic particles that was known as neutron. So neutron was found by James Chadwick, right? So the neutron was found by James Chadwick. So James Chadwick conducted an experiment. He sent alpha particles through beryllium plate and he found a neutral particle that is known as neutron. So we can consider that whatever the absolute charge or relative charge, whatever it is, so the charge is always zero. What is the mass of a neutron? Mass of a neutron is always considered as what? Mass of a neutron 1.675 10 to the power minus 27 kilograms. So this is the mass of a neutron, right? So you have to remember these things, very, very important. Now you can compare the mass of an electron, proton, and neutron, right? So then who you can find out who has the highest mass, right? And if you consider the symbol of neutron, what are the symbol? Symbol of a neutron is actually, we can consider that is N01. You can see that this is the relative charge and this is the relative mass, right? Relative mass and the relative charge. Relative mass and the relative charge. Okay. There are some other particles except neutrons and protons. Yes, you can search that one, right? Rather than addition to these subatomic particles, electrons and protons and neutrons inside the nucleus, there are other subatomic particles as well. Okay. Yeah, mesons, right? There are some names. Okay. Right. Okay. Now remember, I told you that there is only element in the periodic table which does not contain neutron. Who is that? You have to remember that one. There is only element in the periodic table which does not contain neutron. What is that? Hydrogen. That's very, very important. Okay. Right. Now let's quickly summarize everything related to the subatomic particles quickly. Right. Let's revise it quickly. relative charge, then relative mass, and then symbol. If you consider electron, what is the absolute charge? 1.602 10 to the power minus 19 coulomb. Right? What is the absolute mass? 9.107 10 to the power minus 31 kilograms. What is the relative charge? -1. What is the relative mass? 0. What is the symbolization? E minus 1 0, sometimes beta minus 1 0. Then the next one, the next subatomic particle is proton. If you consider proton, what is the charge? Same as electron, 1.602 10 to the power minus 19 coulomb. And what is the absolute mass? 1.672 10 to the power minus 27 kilograms. What is the relative charge? +1. Relative mass, we can consider 1, right? And the symbol P11, if not hydrogen plus 11, right? And the third one is known as electron, proton, neutron. Neutron, what is the absolute charge? 0. Relative charge is also 0. Mass 1.675 10 to the power minus 27 kilograms. And you can see that relative mass is 1. So neutron is symbolized 0, 1. You can understand when you compare the masses of the subatomic particle, students, you can see that the highest mass belong to the neutrons, right? That means mass of a neutron is greater than mass of a proton, and the least mass belong to the electron, right? So the highest mass belong to the neutron, and the second highest one is proton, and the least mass for the electron. Okay, so these are very important. You have to remember. Absolute charge, relative charge, absolute mass, relative mass. These things are very, very, very important, right? So these are the three fundamental basic particles we learn under the topic. Okay, right? Always you should have the summary in your mind. That is very, very important. Right? Okay. Then our next topic was atomic models. Now we know that there are 3 subatomic particles inside the atom. After finding these subatomic particles, now scientists were eager to find out how these subatomic particles are existing inside an atom. So that's how the atomic models are created. So atomic models, a model for an atom, right? Atomic models, right? Can you remember what is the first ever atomic model that they have represented? What is the first atomic model? The first atomic model was Dalton's golf ball model. Dalton's golf ball model. What happened to this? Right? At the beginning, I told you that when you consider the Dalton's golf ball model, actually, after representing these subatomic particles, that means electrons, protons, and neutrons, is what Dalton's golf ball model is actually ignored. That is wrong, right? And then second one was Thomson's plum pudding model. Yeah. Thomson's plum pudding model. Plum pudding model. Right? So under the Thomson's plum pudding model, that he said that atom is look like a positively charged sphere. kind of a sphere like this, positively charged sphere. So inside this positively charged sphere, electrons are actually what? Dipped like plums. That is look like the plums are dipped in the pudding, right? So this is the model of the Thomson's atomic model. So you can see that how what wrong this is, because neutrons are not there. Where is the nucleus? So there are so many mistakes actually inside the Thomson's plum pudding, right? So the main idea about the Thomson's plum pudding is actually he told that negatively charged particles and the positively charged particles exist, right? So atoms look like a positively charged sphere, and electrons are dipped everywhere in the sphere, like plums are dipped in the pudding, right? So this actually we can see that this concept is really wrong. Who proved this one? Who disproved this one? Who disproved the Thomson's model? The next scientist. What was the next model that we need to discuss? Rutherford's. Rutherford's nuclear model, right? Rutherford nuclear model. Or we can say that Rutherford's planetary model. Number 4, Bohr's energy level model. Bohr's energy level model. And then the last one, in modern science, we are accepting quantum model. If not, we can tell that electron cloud model. Electron cloud model, we are accepting that electrons are actually existing as a cloud around the atomic nucleus. So these are the actually five main types of the atomic models. Dalton's Wolfram model, we discussed, that is actually wrong, disproven by Thomson. And Thomson's plum pudding model, as I mentioned you, positively charged sphere, and inside the positively charged sphere, negatively charged particles are dipped everywhere, like plums are dipped in the pudding. And the Rutherford's nuclear model and the planetary model, let's discuss the experiment. And the Bohr's energy level model, somewhat successful model, right? And nowadays we are accepting in the modern science electron cloud model. In order to build up this electron cloud model, Erwin Schrödinger and Heisenberg, so those scientists are actually contributed in order to create this electron cloud model, right? Okay, now we discuss about the Dalton's Wolfram model and the plum pudding model. Now let's go for the Rutherford's nuclear model and let's discuss the experiment, because that experiment is very important, right? Everything you have learned, okay? So we are going to revise them again. Either. Yes, that's what I'm going to do. So Rutherford's nuclear model. Remember, students, actually for this one, Rutherford conducted an experiment. Rutherford conducted an experiment with his two students. So the first one is Geiger, and the next one is Marsden. Geiger and Marsden, right? There were two students actually. With the help of these two students, Rutherford conducted an experiment. This experiment is very famous. This experiment is known as actually Gold-Foil experiment. Gold-Foil experiment, if not alpha particle scattering experiment. So the famous name is actually Gold-Foil experiment, right? So if I draw the experimental setup for this one, so this is that is like this. Look at this one, Ilyu. So here we have kind of a solid lead container. Right. right? So this kind of experimental setup, right? So actually, these are some beam of alpha particles. Right? So this is actually a source of alpha particles. Right? And this is solid lead container. And this is zinc sulfide coated fluorescence screen. Zinc sulfide coated fluorescence screen. So fluorescence screens are using in order to see the radiations properly. So fluorescence screen. Okay. So this is actually thin gold foil. Remember, when they are conducting this experiment, remember alpha radiations. Alpha radiations are passing through this gold foil, and some of the radiations are nicely, right? So penetrating through the gold foil, and you can see the spotted. Here we can see that radiation spots in this way. They are nicely passing through this gold foil, and you can see them in this way. They are spotted like this, right? And some of the alpha radiations are deviated. They have changed their paths, and in this way you can see some spot in the fluorescence spray in this way, right? Some of them are bouncing back in here, right? Here some of them are not penetrating, they are directly bouncing back, right? Some of the particles are moving like this, again going with the direction that they came, right? Look at this. Look at this. You can see three main observations in this experiment. Look at this one. The first experiment was actually alpha radiations are nicely passing through this gold foil without any deviation. So Rutherford and his two students actually implied that, had a conclusion that most of the space in an atom is empty. So that's why these rays are alpha radiations are passing through the gold foil. And then they observed another two observations. If you consider 20,000 particles, one particle out of 20,000 particle, only one particle is deviating, changing the path. That is penetrating, but changing the path, right? If we consider 100,000 of particles, that means 1 lakh of particles, alpha particles, one particle, that means very rarely, one particle is deviating, that means bouncing back. They are not penetrating through the gold foil, they are bouncing back. So they had a doubt why these particles are, some of the particles are penetrating through the gold foil without any hesitation. Some of the particles are penetrating, but they are changing their path, deviating, right? But some of the particles are bouncing back without any what penetrating. Those particles are not penetrating through the gold foil, they are directly bouncing back. So they found the reason for these things. The first reason is actually why these most of the particles are penetrating through the gold foil. The reason is the most of the space in the atom is empty, right? And for other two observations, they found the conclusion for that one also. The reason is actually atomic nucleus, because we know that in the Rutherford's, this is Rutherford's nuclear model. So the previous atomic model was Thomson's model, because in the Thomson's model, he didn't discuss anything regarding the nucleus, atomic nucleus. He didn't say anything about the nucleus. But Rutherford said that like this, okay? This diagram is okay, right? Try to get an idea, very simple, okay? One more thing I want to remind you that why we are using a solid lead container. Remember, alpha radiations are very harmful, right? So they have ionizing power, the highest ionizing power. So therefore, alpha radiations are harmful. Therefore, we are using solid lead container in order to prevent from the radiations, because these experiments are conducted by humans, right? So these people actually humans like us. So therefore, they followed some precautions. They use their solid lead container in order to prevent from the radiations, right? So try to understand. And alpha particles are known as what? Nothing else, helium nucleus. Helium 242 plus. Helium nucleus. So alpha particles are positively charged, right? Okay. Now I'm going to explain that remaining two observations, why some of the particles are deviating, penetrating and deviating, and some of the particles are bouncing back. Look at this one. Students, atomic nucleus is positively charged. Atomic nucleus is positively charged. Just imagine this is the one of the nucleus we have in nuclei we have inside the gold foil. If the alpha particles are, if the alpha radiations are coming towards this particle in this way, look at this one. These are the alpha radiations. These radiations are moving through the gold foil without any issue. But now look at this one here. Some of the radiations are very close to the nucleus. So we know that alpha particles are positively charged. Since the alpha particles are positively charged, atomic nucleus also positively charged, they are changing their path. That means some kind of a repulsion force. Repulsion force is created. Look at this one. When the alpha particles are getting closer to the nucleus, they are repelling. They are repelling. The repulsion force is created. Because when positive meet each other, what will happen? They will repel. Same charge. Now just imagine some of the particles are directly coming towards the positive particle. Oh my God, what will happen? So they are deviating with high speed. They are deviating with high, that means a very large angles. Some of them are directly bouncing back in this way. You go back again, likewise. Because positive, they do not meet each other, right? They will repel. That is the reason very rarely some particles are deviating, penetrating and deviating. Some of the particles are bouncing back. So these particles are no issue because they are a little bit away from apart from the nucleus. They are nicely going through the gold. So Rutherford concluded that there is a small area. There is a small positively charged area that is known as atomic nucleus. That is the most important thing that we have to discuss related to the Rutherford's nuclear model. That's why I told this one as Rutherford's nucleus, right? He's the person actually who found the atomic nucleus, the existence of the atomic nucleus, right? So there is a point mass confined area, positively charged one. So that is the atomic nucleus. Inside the atomic nucleus only, we have protons and neutrons, right? So that is the main contribution from the Rutherford's nuclear model. And Rutherford said that, like planets are orbiting the sun, electrons are also orbiting the atomic nucleus. So that's why we consider this one as Rutherford's planetary model. Try to understand, right? And the next thing is, he told that this atomic nucleus is very small. Can you remember that football ground example, right? In theories also, I mentioned you that if you keep a bean at the middle of the football ground, that bean is what? Atomic nucleus. And the surrounding area in the football ground is the area that electrons are existing. That means you can consider that is the size of atom. Now you can compare the size of the atom and the atomic nucleus, right? The bean at the middle of the football ground, that is the atomic nucleus. And the remaining surrounding area of the football ground is what? Size of the atom. That means the area that is existing in the electrons. So you can compare the size of atomic nucleus and the atom. Very small, right? Atomic nucleus is very small. So try to understand, atomic nucleus is small area. Inside that small area, neutrons and protons are existing. Around the nucleus, electrons are existing. That's all, right? That is all about the Rutherford's nuclear model. Done. Right. What is the next model that we have to discuss? Yeah, Bose model. Okay. Right. So the next model is Bose model, Bose energy level model. Remember, students, remember when we go for the Bose energy level model, Niels Bohr, there was a scientist known as Niels Bohr. So Niels Bohr said that, so this is the atomic nucleus. Around the atomic nucleus, there are some certain paths, right? Certain path that the electrons are existing in this way. These are some paths where electrons are existing. So these paths are known as orbits or else energy levels, right? Energy levels. Remember, these are hypothetical things, okay? N equal 1, N equal 2, N equal 3, N equal 4. So likewise, we have what? Energy levels. So these are the energy levels of the atom, right? So this is the main idea about the Niels Bohr energy level model, right? So he told about the some kind of a location of an electron, right? Right. And the most important thing that he said regarding the energy level model, if you take if you cut in this way the energy levels, and if you take an area in this way, so these are the energy levels. Normally, when we are going far away from the atomic nucleus, the gap between the energy levels are decreasing in this way. Okay. This is n equal 1, 2, 3, and this is n equal 4, right? Likewise, gap is decreasing. So remember, when one electron is moving for high energy level, when one electron is moving for the high energy level, it absorbs the energy, right? Absorb the energy. When an electron is moving from high energy level to low energy level, so they emit the energy, release the energy. Remember, they absorb or emit the energy as electromagnetic radiations. The energy of the electromagnetic radiations can be calculated using E equal h nu equation, right? So remember, these are photons, right? These electromagnetic radiations are carrying the energy as photons, right? Energy of a photon. Energy of a photon is calculated by E equal h nu Planck's constant multiplied by the what? Frequency of the corresponding electromagnetic radiations, right? We are going to discuss this one again. So try to understand, this is main idea. When the electrons are moving for the high energy levels from the low energy level, they absorb the energy. When the electrons are moving from high energy level to low energy level, they emit the energy, right? Low to high, absorb the energy. High to low, they emit the energy. So try to understand. This is the main concept regarding the Niels Bohr model, right? And we know that how to symbolize an atom, right? So when we are symbolizing the atom, this is actually atomic number, and this is the mass number, right? We know about these things. You have learned these things in your O-level time also. So this is atomic number. and this is mass number. So atomic number is calculated by number of protons, right? And the mass number is calculated by number of neutrons plus protons. Very easy, right? So these are the three subatomic particles and the atomic models we have to remember. These are the basic theories that we have learned. Got it? Very, very important. Right. So the next topic that we discussed was isotopes. The next topic that we discussed was isotopes. So isotope means actually for the same element, same number of protons, right? Same number of protons. That means atomic number is same, but different mass numbers are there. For example, if you consider hydrogen, what are the isotopes of the hydrogen? We discussed these things, ne? Isotope means same atomic number, but different mass numbers. Right? So example, we can consider hydrogen isotopes. What are the three main types of hydrogen isotope? Protium, deuterium, tritium. Ne? Protium, deuterium, tritium. H11, protium, H12, deuterium, H13, tritium. Right? Look at this one. Number of electrons, protons and neutrons. Number of electrons are same, 1, 1, 1. Number of protons, same, 1, 1, 1. But if you consider number of neutrons, 0, 1, 2 here. So we know that mass number is obtained by taking the summation of protons and neutrons. So here 2, this is 3. That's how we obtain the mass number of these isotopes, right? Same atomic number, different mass numbers are known as isotopes, right? And we discussed there are two types of isotopes: stable isotopes, stable and unstable isotopes. Unstable means they are emitting some radiation, so therefore these are known as radioisotopes. Radioisotopes. Got it? Very important. Same number of protons, that is same atomic number, but different mass numbers. Those are known as what? Isotopes. And then we discuss about the relative abundance about the isotopes. Relative abundance. Students, what does mean by the relative abundance? Relative abundance. Relative abundance means the percentage value that exists in the nature by the isotope, right? So that means we can consider that if you consider the three isotopes of hydrogen, how much of percentage value, right? What is the percentage value of protium in the atmosphere, right? We can consider, for example, this is 75%, right? This is 75%. This is 20%, and this is 5%, right? So these are some hypothetical values. Okay, these are not correct values. So these are the relative abundance. Relative abundance means the percentage value that exists in the nature by that isotope. 75% of the hydrogen atoms, if you consider hydrogen sample, 75% is what? Protium. 20% is deuterium and 5% is tritium. So likewise, we can consider the relative abundance of the isotope. Remember, students, using the relative abundance, we can say that whether this isotope is what? Stable or not, right? Whether it is stable or not, right? The relative abundance value is high in protium. So therefore, we consider this is very stable. These are not that much stable. Who is the unstable? Who is the most unstable isotope there? Tritium, right? The stable isotope is protium. Unstable one is tritium. Got it? Very easy. Right, okay. Right. If you consider the isotopes, chemical properties are same. Chemical properties are similar, but physical properties are different. Remember, if you do the past papers, actually you will meet this one. Physical properties are completely different because mass is changing. For the chemical properties, the only affecting factor is electron, right? And the next thing is sometimes you can find out the average relative atomic mass of an atom using the relative abundance and the corresponding isotope, right? So we discuss some questions regarding the isotopes. So let's consider one question, right? Simple question. They have given that isotope and the relative abundance. And this is relative abundance, right? And the isotope is chlorine 1735. This is chlorine 1737. The relative abundance values are given as 75%, 25%. Then you can find out the average relative atomic mass, right? Average relative atomic mass of chlorine. However, we know the isotope. Mass number is 35. You can multiply this 35 mass number from the relative abundance value, that is 75. Plus, if you consider the next isotope, that is 37. 37 multiplied by 25 divided by total value 100. Right? So if you simplify this one, we can take that 25 as a common factor for this one. So this is 35 into 3 and this is 37. So this is 1 over 4. 35 into 3. 15, 105, 142. 142 divided by 4. So this is 271. 71 means 35.5. When we are doing the calculations for the relative atomic mass, we are taking for the chlorine, that is 35.5. If you know the relative abundance and the isotope mass number, you can find out the average relative atomic mass of that particular element. So these are the things actually we discuss about the isotopes. Very easy, right? Nothing. And we did some calculations in the theories. So you can practice those calculations again, because those things are given in the tutorial. Okay. Right. Okay. So the next topic is location of electron. When we talk about the location of electron, actually, there are two things to remind you, but let's see. Location of an electron. Before this, actually, we have to discuss about the de Broglie's equation. De Broglie's equation. So what is the de Broglie's equation? De Broglie's equation is lambda equal h over mv, where lambda is the wavelength, and h is the Planck's constant. What is the Planck's constant value? Planck's constant value is 6.626 10 to the power minus 34 joule seconds. And then simple m means mass, and v is the velocity. Right? So this de Broglie's equation can apply for the electrons also. Remember, students, de Broglie's equation can be applied for the electrons also. Since we can apply the de Broglie's equation for the electrons, we consider that electrons are having the duality nature, right? Electrons have duality nature. What does mean by the duality nature? Duality nature means they can behave as particles as well as waves. Wave nature and particle nature. We discussed this one in the cathode ray experiment also. J.J. Thomson already proved this one. Can you remember? When we keep that metal cross, he observed the image of the metal cross. And if you keep the paddle wheel started to rotate. So they are implying particle nature and the wave nature of the electrons, right? So try to understand, this is very, very important. Electrons are having both particle nature and wave nature. Remember, students, so this is de Broglie's equation. Remember, lambda equal h over mv. Lambda means wavelength, right? H means Planck's constant, 6.626 10 to the power minus 34 joule seconds. M means mass, V means velocity, right? Okay. Now look at this one. In order to find out the location of electron, there are two methods in our syllabus that they have given. Number one is spectrum analysis. Number one is spectrum analysis. Number two is ionization energy analysis. Ionization energy analysis. Under the spectrum analysis, we are going to talk about the electromagnetic spectrum. First of all, we have to discuss about the electromagnetic radiation. Remember, spectrum means, students, what? A set of electromagnetic radiations. Right? Spectrum means electromagnetic radiation. Can you remember I told you that under the Niels Bohr atomic model, so electrons are actually gaining electrons and jumping for the high energy levels. And those electrons are coming back to the low energy levels while releasing the energy. Right? So we can calculate that energy using the equation equal h nu. Right? Equal h nu. This is very important. Remember, this is the energy of a photon. E means energy of a photon. Energy of a photon. Right? What is H? H means Planck's constant. Planck's constant. The value is 6.626, 10 to the power minus 34 joule seconds. And nu is the frequency. Frequency. Nu. That is Greek letter. And remember, we have another equation. We have learned this one in our O-level time also. What is that equation? C equal nu lambda, right? If I take this one as the second equation and this one is the first equation, you can subject here nu equals C over lambda. Then substitute for the first equation, then you are getting another equation E equal HC over lambda, right? So in the calculations, we can use the equation, right? So this is energy of a photon, right? If you multiply this equation equal HC over lambda from capital L, if you multiply this one by capital L, so this is considered as energy of a photon mole. Energy of a photon mole. If you multiply this one by Avogadro's number, L means Avogadro number. This is Avogadro constant. Avogadro's constant 6.200 10 to the power 23 per moles. Right? So that is known as energy of a photon mole. So try to understand under the electromagnetic spectrum is nothing else, a set of electromagnetic radiations. We can calculate the energy of electromagnetic radiation using this equation. E equal H mu, okay? Right. Right. Okay. If you go for the electromagnetic spectrum, we discuss what is the electromagnetic spectrum. we are starting from the radio and TV waves. Right? Radar waves. Okay. Microwaves, infrared radiations, right? And then we have visible light, right? So this is visible light. And then we have ultraviolet radiation. And then we have X-rays and gamma rays, right? So if you go for the visible light region, so we can have 7 colors. You know that what are the 7 colors we have? So we can go one by one. Red, orange, yellow, green, blue, indigo, violet. Okay, so these are the colors, and we know that for this direction, frequency nu increases, wavelength lambda decreases. Wavelength lambda decreases. Okay. This is the way. So this is electromagnetic spectrum. So spectrum means actually what kind of a set of electromagnetic radiations, right? Right. Okay. So we can find out the location of electron using the spectrum. So when we talk about the spectrum, electromagnetic spectrum is very important. So that's why I mentioned that one there. Now look at this one. When you consider the spectrums, there are 2 types. The first one is continuous, and the second one is discontinuous. Continuous. For this one, we are giving line, or else we are giving another name, discrete. Okay. So for the continuous spectrum, the nice example is what? Electromagnetic spectrum, right? That we discuss. Electromagnetic spectrum is a continuous spectrum. Remember, students, continuous spectrum means actually all the energy radiations are included. Okay. In a particular wavelength range or frequency range, all the energy radiations are included, right? But in the discontinuous one, so only few radiations are included. So that's what we are going to analyze in order to find out the location of electron. So the first discontinuous type is atomic absorption spectrum. So the second type we are learning, atomic emission spectrum, right? Atomic absorption spectrum and atomic emission spectrum. So these are the two types of discontinuous spectrum we have to discuss. So using the discontinuous spectrum only, we are going to find out the location of electrons, right? So there are two types of spectrums, continuous and discontinuous. Continuous example is electromagnetic spectrum. For the discontinuous, we have two types, atomic absorption spectrum and the atomic emission spectrum, right? We can derive the atomic absorption spectrum using an experiment. We discussed that experiment in the theories, but that experiment is not that much important, but idea is important. Atomic absorption spectrum. In atomic absorption spectrum, what happens is hydrogen atoms, we are taking hydrogen atoms as the reference atom. Hydrogen atoms are, right? Very easy. Look at this, Anil. So this is one of the important topic, hydrogen emission spectrum. Let's take a break after the discussion of the hydrogen emission spectrum. Okay, let's have a small break and let's again start. If not, that's very difficult to concentrate. Right. Very easy. Just go through these things, everything we have learned. So this will be nice revision for you to revise all your knowledge. Okay. Yeah. You can have the recording. Don't worry. I'll give you the recording. Don't worry. So atomic absorption spectrum. Under the atomic absorption spectrum, actually hydrogen atom is absorbing the energy. Right? Look at this one. Here in this way, there are some certain energy levels. So in this way, there are some certain energy levels. Right? This way. Okay. N equal 1, N equal 2, N equal 3, N equal 4, N equal 5. Remember, when the energy levels are far away from the nucleus, the gap is decreased. Absorption spectrum is obtained when the electrons are moving from lower energy level to high energy level. Just imagine, electron is moving from the hydrogen's first electron is moving from the first energy level to the fifth principal energy level. And then the next electron means the second possibility, the electron is moving from the first principal energy level to the fourth one. And then another possibility, same electron can be moved from the third principal energy level, and N equal 1 to 2, right? Look at these transitions, right? N equal 1 to 5, 1 to 4, 1 to 3, and 1 to 2, right? These are the transitions. N equal 1 to N equal 5. And this is N equal 1 to N equal 4. And this is N equal 1 to N equal 3. And this is N equal 1 to N equal 2. So likewise, there are some electron transitions. So remember, I told you that according to the Bohr's model, I told you that when the electrons are moving from low energy level to high energy level, they are absorbing the energy because energy is very high. Since the energy is very high, they should absorb the energy. So therefore, we can have a line diagram. That line diagram, experimentally we can observe that one. Experimentally we can observe that line diagram, that is known as spectral line diagram. This is energy level diagram. Okay, this is energy level diagram. We can obtain the spectral line diagram for the electrons. Spectral line diagram. How is that? Spectral line diagram. So here we can see that corresponding line for this one. in this way. We know that highest energy belong to n equal 1 to 5. Second highest energy belong to n equal 1 to 4. Third highest energy belong to n equal 1 to 3. N equal 1 to 2 is the least energy. So therefore, we consider that energy and frequency increase for this direction. And wavelength lambda decrease for this direction. Decreases. Okay. For this direction, energy and frequency increase and lambda wavelength is decreasing. Can you understand? So this is known as atomic absorption spectrum, energy level diagram, and the spectral line diagram. Very easy. So likewise, when the electrons are coming back to again the ground level, that means the principal energy level number 1, we can obtain the emission spectrum. Absorption spectrum means the spectral line diagram, the energy diagram that we are having when the electrons are moving for the high energy levels. When the electrons are coming back to the low energy level, we are considering what? Emission spectrum. Atomic absorption spectrum and the emission spectrum, right? Let's know the emission spectrum. Emission spectrum. Atomic emission spectrum. Emission spectrum. Look at this diagram. Right? N equal 1, 2, 3, 4, 5. Now look at this one. Electrons are moving from high energy levels to low energy levels. Electrons are moving from high energy levels to low energy levels in this way. Right? You can observe this kind of a energy level diagram, right? If I draw the spectral line diagram is look like this. Here, in this way. Here we have another line, right? So, energy level diagram. And this is the spectral line diagram. Right? Look at this one. Electron transitions are from n equal 5 to n equal 1. N equal 4 to n equal 1. Electrons are coming back to the low energy levels. They are releasing the energy, right? N equal 3 to n equal 1. N equal 2 to n equal 1. Right? Can you understand? Okay. So normally, these are considered as actually bright lines. Bright lines in a dark background. Okay. So in the previous one, I forgot to write down that is dark lines in the bright background, because here actually they are releasing the energy, emission spectrum means they are releasing energy. So therefore, these are bright lines. If the energy are absorbed, these are considered as what? Dark lines. Okay. So this is the difference between the emission spectrum and the absorption spectrum, right? So why we are studying this spectrum? In order to find out the location. Location means these spectrum data values are giving us that energy levels, existence of the energy levels. Electrons are moving here and there between the energy levels. So these are some certain paths, right, that electrons can exist. Electrons can move for the second principal energy level, third one, fourth one, right? So likewise, there are some certain energy levels. So actually the emission spectrum analysis. So the next one we are going to discuss is hydrogen emission spectrum. So under there, we are going to learn that hydrogen emission spectrum is proving the Bohr's theory, right? So that's the simple idea. Okay, right. I'll give you 15 minutes, okay? A break, 15 minutes break. After break, let's again start the session, second session. Let's finish all the theories, important theories that we need to discuss, okay? Okay, quickly have a break, 15 minutes, okay? After 15 minutes, I'll start the session. Right, okay. Then let's start again. So look at this one. So we were talking about the emissions absorption spectrum and the emission spectrum. So the next topic is actually hydrogen emission spectrum. Right? Hydrogen emission spectrum. This is very, very important. Emission spectrum. In recent past paper, they have given first MCQ using the hydrogen emission spectrum, right? If you draw the energy level diagram of the hydrogen emission spectrum, first of all, right? So finally, we can see that the Niels Bohr concept is correct, because Niels Bohr said that energy levels are existing. Electrons can move here and there between the energy levels. So that concept is proven by this emission spectrum. Let's see. These are some energy levels. Right? N equal 1, N equal 2, 3, 4, 5, 6, and 7. We know that, right? Look at this one. So in the hydrogen emission spectrum, we can see some several series, right? So if you consider N equals 7 to N equal 1, it's look like this, right? Electron is moving from the 7th principal energy level to the 1st principal energy level. And here we can see electron is moving from the 6th principal energy level to the 1st principal energy level. And then 5 to 1. And then 4 to 1. 3 to 1. And 2 to 1. Look at the electron transitions. Remember, these are electron transitions. All the electron transitions that are falling to the 1st principal energy level considered as Lyman series. This is Lyman series. Lyman series belong to the ultraviolet region in the electromagnetic spectrum, right? Lyman series belongs to the ultraviolet region in the electromagnetic series. So therefore, we can't see that one, right? Ultraviolet radiations are not sensible for our naked eyes. We can't see them. So therefore, these are the Lyman series. Look at the electron transitions, right? So you can see when you analyze the electron transitions, the highest energy belongs to the N equals 7 to N equal 1. Look at the gap. The highest gap belongs to N equals 7 and N equal 1. So therefore, the electron transition, right? So the highest energy released from the electron transition N equals 7 to N equal gap, N equal 1. So you can look at the gap and understand that. Now, all the electron transitions that are taking place, the 1st principal energy level is known as Lyman series. If you go for the Balmer series is look like this. So this is the Balmer series. All the electron transitions that are taking place to the 2nd principal energy level is considered as the Balmer series. So this is Balmer series. All right. So this is Balmer. This is Balmer series. Remember, the very first 4 spectral lines in the Balmer series belong to the visible light, right? Very first 4. But here I'll write this one is related to the ultraviolet region. Let's see, okay, what is the reason behind that. Now, if you consider the Balmer series very first 4 spectral lines, first one is known as H alpha. So this line is known as H alpha. H alpha is red color. We can see that. So these are the only 4 radiations we can see in the hydrogen emission spectrum for our naked eye. Because Balmer series, the very first 4 spectral lines are belong to the visible light region, H alpha. And then next one is H beta, that is green color. H beta, green color, second one. And the third one is H gamma. H gamma, that is blue color, right? That is blue color. And the fourth one is H delta, that is violet color or purple color, violet or purple color. So we know that if you go for the electromagnetic spectrum that we discussed, in the electromagnetic spectrum, we know that visible light region is starting from the red color and ending up with the violet color or purple color. So therefore, after the violet color, we can't continue the visible light region. So therefore, we have to go for the next electromagnetic radiation type, that is ultraviolet. So therefore, remember, very important this one, right? Very, very important. Even though we typically, generally we say that Balmer series belong to the visible light region, but that's not completely correct, students. Remember, the reason is very first 4 spectral lines are what related to the visible light region. That is okay, fine, right? You can see the colors: red color, green color, blue color, and violet color. So after the violet color, so there are many electron transitions, right? So not only these 4, there are many electron transitions that we can continue for the Balmer series. So therefore, those possible electron transitions are belong to the ultraviolet region. The reason is H delta violet color is ending with the what? Visible light region. Visible light region is ending with the violet color. So these are belong to the ultraviolet region, right? So you have to keep that in your mind. The next one, the next series, all the electron transitions that are falling to the third principal energy level. So that is considered as Paschen series. So this is Paschen, right? Look at this one. This is Paschen. Paschen series belong to the IR region. And then all the electron transitions that are possible for the fourth principal energy level, right? So these are what? Bracket. This series is known as bracket. So this is also belong to the IR region. And then all the possible electron transitions for the fifth principal energy level. This is fund series, PFUND fund, that is also related to the IR region, right? Lyman, Balmer, Paschen, bracket, and fund. Lyman, all the electron transitions are to the first principal energy level. Balmer, all the electron transitions are belong to the second principal energy level. Paschen, third, bracket, fourth, and fund, fifth. Right? So you can see the line energy level diagram. Look at the energy level diagram. Now, when you analyze this diagram, you can see that highest energy for the highest frequency, we learned that equation E equal H nu, right? Or we can say that E equal Hc over lambda. Energy, right? Energy corresponding, these electron transitions are representing that electrons are falling to the lower principal energy levels, they are releasing the energy, right? They have released the energy. So these electron transitions are representing that electrons are falling to the lower principal energy levels and they have released the energy. So therefore, these energies are directly proportional to the frequency and the inverse proportional to the wavelength. So therefore, we can say that which line has the highest frequency or highest energy? Which line has the highest frequency or highest energy? Highest energy belongs to the n equals 7 to n equal 1. Therefore, we can say that for this direction, energy and frequency both are increasing, right? So what happened to the wavelength? Wavelength is increasing for the other direction. For this direction, wavelength is increasing. Lambda increasing. Try to understand, okay? Because the highest gap belongs to the n equals 7 and n equal 1. So try to understand, this is Lyman, Balmer, Paschen, bracket, and fund. hydrogen emission spectrum. As a summary, you have to keep this one in your mind always. Very, very important. Got it? Very, very important. Right? So actually, hydrogen emission spectrum is proving that Niels Bohr concept is correct, idea is correct, because energy level concept is okay, fine, we can accept. Electrons are moving between the energy levels. They are moving for the high energy levels to absorb the energy, coming back to the low energy levels by releasing the energy. So they are releasing the energy as electromagnetic radiations. We can calculate the energy of those electromagnetic radiations using E equal hc over lambda. Got it? So that's the way. Right? Easy. This is very easy. Some lines in the Balmer series belong to the ultraviolet region. We know that. Can you remember in the electromagnetic spectrum, I told you that visible light region is ending up with the violet color, right? Red color, uh, orange color, yellow color, green color, blue color, indigo, violet. These are the 7 colors in the visible light region. So the last line, that means the fourth line, is ended up with violet color, that means purple color. So can we continue here after visible light region? No. So therefore, the very next spectral line, very next electron transition in the Balmer series belong to the ultraviolet region, because after the electromagnetic series, after the visible light region, we have the ultraviolet region. Okay, very easy. Yeah, don't consider the gap between the series, but here I have keep some gaps between the lines in each series. This is to represent that energy level gap is decreasing. Look at this one. Here, from here to here, energy level gap is decreasing near. In order to represent that one, I have mentioned the spectral lines gap, electron transition gap is also decreasing in order to represent that one, right? Nothing else. In your resource book, they have given the spectral lines, but without considering these gaps, they have given what? Same gap. So here I have mentioned this gap. The reason is I wanted you to understand that energy level gap is decreasing. Okay, so that's why I have mentioned that one in the electron transitions also. That's all. Right? Usual theory class start at 8 p.m. to we are conducting that one to 11 p.m. So today I started this one in order to revise these theories again. Okay, right. So don't worry about the time and everything. And so why you are worrying about the time? Hmm? I told you, Saturday is for chemistry day. After 6 p.m., after 5 p.m., separate that time for the chemistry. Okay. So you are joining for the online classes. So you can stay at home and nicely what? You can watch these things, right? And thank God we have the class in Saturday. Sunday morning, you are free, right? You don't have schools. If you have classes, normally classes are starting at 8, 9 again, right? So therefore, don't worry, right? Don't worry about the time. If I continue the class until 12, doesn't matter for you, right? This is all about your involvement, right? If you don't have in your involvement for the subject, actually you are not suitable to do the A-level examination, right? Look at this one. Now we did the energy level diagram. Now we are discussing the spectral line diagram, right? Look at the spectral line diagram. Spectral line diagram is also same as the energy level diagram, right? In this way, we can draw that one. So look at this one, Lyman. This is Balmer. Parshan. Bracket. And this is 1. Right? Lyman. Balmer. Parshan. Bracket. 1. Okay. And we know that this is H alpha, H alpha, H beta, H gamma, and this is H delta, right? So we know that for this direction, energy and frequency both are increasing, right? While lambda wavelength decrease. So this is the spectral line diagram. So try to understand, this is the way. Okay. Hydrogen emission spectrum is proving that Niels Bohr theory is correct. Perfectly all right. Right. Okay. Now let's go for the ionization energy analysis. Before we go for the ionization energy analysis, I want to remind you that there were two scientists actually known as Peter Zeeman and Johannes Stark. So these two scientists conducted some experiments that these spectral lines actually can be split again into the sub lines, right? So actually the first name is actually Peter Zeeman, right? So Peter Zeeman tried that. Peter Zeeman, he sent these spectral lines through the magnetic field, and then he observed that these energy levels are again splitting into sub energy levels. Here comes the sub energy level concept. Sub energy levels, right? So this is known as actually Zeeman effect. Zeeman effect. Zeeman effect, right? And likewise, there was another scientist. His name was Johannes Stark. Yes, we have to write down the names properly. Johannes. Yes, Johannes Stark. Johannes Stark, he used an electric field. Using an electric field also, these energy levels are again splitting into sub-energy levels, right? So that is known as what? Stark effect. Zeeman effect and Stark effect. Okay. So this is about the what? Sub-energy level concept, right? Energy levels can be split into sub-energy levels. So we know what are the sub-energy levels we have to discuss. SPDF, likewise, we have to discuss about the sub-energy levels, right? So try to understand, this is also very important. This is all about the spectrum analysis. Spectrum analysis are proving actually the energy levels are existing. These electrons are moving between the energy levels. They are moving to the high energy levels by absorbing the energy. They are coming back to the low energy level by releasing the energy. Right? Okay. Right. Now let's go for the ionization energy analysis. Right. What does mean by the ionization energy? Right. Ionization energy. What does it mean by the ionization energy? Ionization energy means simply we can say that is the atom, right? There are some certain energy levels. Just imagine this is the valence shell. In the valence shell, there is an electron. In order to remove an electron, we need to supply the energy. Because remember, students, this electron is attracted towards the atomic nucleus from the nuclear attraction force. So, ionizing means we have to remove this electron against the nuclear attraction force. That means we have to supply energy against the nuclear attraction force in order to remove this electron. That corresponding energy, that related energy is known as what? Ionization energy. For the ionization energy, there is a lengthy definition, but I will explain that one from an equation, very easy. First of all, let's go for the first ionization energy. First ionization energy. First ionization energy is defined as, so this is I1. This is defined as, if I take a metal atom, M gas, we are removing one electron from this one to form M plus gaseous state cation. So it's remove one electron in this way. So this is first ionization energy. Look at the definition now. Listen to me, right? Listen to me carefully. The minimum energy that is required to remove 1 mole of electrons, 1 mole of electrons from 1 mole of gaseous state neutral atom in order to form 1 mole of gaseous state single valence cation at the standard state temperature and pressure is known as the first ionization energy. I will repeat once. The minimum energy that is required to remove 1 mole of electrons from the gaseous state neutral atom in order to form 1 mole of gaseous state single valence cation at the standard state is known as first ionization energy. Why particularly gaseous state? We know that if you compare the states of matter from the gaseous state, we can easily remove the electrons because particles are randomly moving here and there. The gap between the particles are very low. Easily you can pick up an electron, right? Not unlike solids and liquids, right? If you go for the second ionization energy, look at this one. Second ionization energy. Second ionization energy is known as I2, right? I2. Remember, second ionization energy means we are removing 1 electron from that single valence cation, not from the neutral atom, right? Because some of the students are thinking that we are removing 2 electrons at once. That is wrong. That is completely wrong, right? Second ionization energy means after removing 1 electron from the neutral atom, it's forming single valence cation. From that single valence cation, we are removing another electron. The definition for the second ionization energy is, right? Look at this one. The minimum energy that is required to remove 1 mole of electrons from single valence cation, gaseous state cation, in order to form bivalent or divalent gaseous state cation at the standard state is known as the second ionization energy. Sir, then what about this one? If you are removing directly 2 electrons from the atom, then what it should be? If it is not the second ionization energy, what is that? So this is actually I1 plus I2, summation of the first ionization energy and the second ionization energy, right? Try to understand. Okay, so this is all about the ionization energy concept. Now, ionization energy concept, how that is related to find out the location of electron. Remember, we can easily analyze the ionization energy graphs to find out the location of electrons. We know that, students. Now, we know the main location of electrons. What is the main location of electrons? Niels Bohr already said that the main location of electron is energy levels, right? And then using the Zeeman effect and Stark effect, we found that. So they are telling that sub-energy levels are also existing, right? So now we can prove that sub-energy levels are existing by analyzing the ionization energy graph. right? So I'm going to draw the ionization energy graph for a particular element. I'll take a phosphorus, right? Then you will see that sub-energy levels are existing, right? Shall we go for the graph? We are going to analyze some ionization energy values, and we are going to tell that these are the exact location of electrons. That means we are moving further, we are moving a deeper uh, to find out the location of electrons. Sub-energy levels, energy levels, sub-energy levels, right? Later we are going to discuss about the orbitals, and then we are going to discuss inside an orbital there can be 2 electrons, maximum 2 electrons. Hund's rule, Pauli's exclusion principle, everything we are going to learn. Can you understand? Right? Now look at this one. Easy. These things are nothing. Now you can see that we are going to analyze the ionization energy graph of phosphorus. How many electrons are there in phosphorus? How many electrons are there? I will write down the configuration for the phosphorus. We are going to discuss the electron configuration also, don't worry. But now just remember this one, 1s2, 2s2, 2p6, 3s2, 3p3. You know, right? We learn how to write down the electron configuration. 1s2, 2s2, 2p6, 3s2, 3p6. When you look at this electron configuration, these 5 electrons are belong to the third principal energy level. These 8 electrons are belong to the second principal energy level, and these 2 electrons are belong to the first principal energy level. Right? So therefore, if you are drawing the atom in this way, so this is the atom, right? There are 2 electrons in the first principal energy level. There are 8 electrons in the second principal energy level. And there are 3 electrons in the third principal energy level. Right. Now look at this one. In. So n equal 1 to 15. Okay. N equal 1 to 15 because there are 15 electrons. We are considering the consecutive ionization energies. I1, I2, I3, I4. Likewise, we are going to remove these 15 electrons one by one. Okay. We are going to remove the 15 electrons one by one. Let's see what will happen. So look at this one. There are 3 electrons, right? Right. Okay, we can draw the graph in this way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. Here we have three electrons, right? So they are increasing, okay? You can see that ionization energy is increasing, okay? Little by little, it's increasing. They are not in the same horizontal place. And then we are suddenly moving to the second principal energy level. That means this level. Right. and then these two jump. Here to here we have small jump, right? And then you're right. Right. Okay. This is the graph. We can find out the ionization energy and we can plot a graph in this way. Okay. Now look at the graph. So this is I1, I2, I3, I4, I5. I6, 7, 8, 9, 10, 11, 12, 13. Right. And this is 14 and I15. Now look at this one first. Now you can see that one by one we are removing electrons from the valence shell. We are started from the valence shell, right? So we can easily remove the electrons from the valence shell because the nuclear attraction force felt by the valence electrons are low. So therefore we can easily remove the electrons. Look at this one. We can easily remove these 3 electrons one by one. We are removing. And one more thing you have to understand here, they have unique ionization energies, right? If you are removing this electron, even though that they are existing the same principal energy level, they have unique 3 separate ionization energies, I1, I2, I3. You can see here, in here we have slightly large gap. Okay, slightly large gap. Okay, and here also we can see that kind of a slightly large gap. Large gap. But remember, if you go for this one, this is actually very large gap. This is very large gap. And here also we have a very large gap. Right? Students, you have to understand that when you analyze in this graph, you can see that there are 2 very large gaps. Those are indicating that we are jumping to the next principal energy level. Here in the last principal energy level, there should be 5. In the last principal energy level, there are 5 electrons. After removing these 5 electrons, we have to go for the second principal energy level. So therefore, the distance for the second principal energy level is very low. Third principal energy level and second principal energy. If you come to the second principal energy level, the distance is very low. So that means the nuclear attraction force felt by those electrons are very high. So that's why their ionization energies are very high. So you can understand by analyzing this graph, after removing these 5 electrons, these 10 electrons are belong to the second principal energy level. And again, you are obtaining same kind of a very large gap because after removing these 8 electrons, we are moving for the first principal energy level. First principal energy level. Right? So therefore, we can understand that. So by looking at the very large gaps, we are moving for the principal energy level to principal energy level. Right? N equal 1, there are 2 electrons. First principal energy level, right? You are moving from the second principal energy level to third one, you will obtain very large gap. Okay, already we know about that one. Principal energy levels are existing. We know about that one. We learned that one in the Bohr's diagram, and we proved that one in the emission spectrum. Now that's not the case. Here you can see very large gaps. Sorry, slightly large gap. What does mean by this slightly large gaps? Slightly large gaps are indicating that inside the principal energy level we have sub energy levels. Can you understand? Remember, this is actually P3. Look at this one. 3P3. P sub energy level. P sub energy level in the third principal energy level. These two electrons are belong to another sub energy level, that is S. These 6 electrons are belong to the P sub energy level. These 2 electrons are belong to the sub energy level. And here in the first principal energy level, we have only 2 electrons that is belong to the S sub energy level. So these slightly large energy gaps are indicating that inside the energy levels, sub energy levels are existing, right? So by analyzing the ionization energy graph, we can understand that each and every electron, after removing each and every electron, we can obtain unique 15 ionization energies for the phosphorus atom, right? Even though they are existing in the same principal energy level, look at the 5 ionization energy values. They are different from each other. Others also same way, right? And the next thing is very large gaps are obtaining when you are moving from principal energy level to another principal energy level. Slightly larger gaps are obtaining when you are moving from simple sub energy level to another sub energy level. So ionization energy graph, analysis of ionization energy graph is explaining that the existence of the sub energy level. Try to understand what I'm saying, right? So we should know what are the sub energy levels existing, right? So I will draw a table, then you will understand what are the sub energy levels that are existing, right? Look at this one. Now we know about the energy levels. Let's go for the sub energy levels. Right? Principal energy level. N. And then we can go for the sub energy levels. Right? Sub energy levels. Right? And then we can consider how the electrons are filled. How the electrons are filled. And then we can consider total number of electrons. Total number of electrons. Right? If you consider the first principal energy level, remember students, there is only one sub energy level, that is S. Okay. There is only one sub energy level, that is S, right? Inside the sub energy level, there can be only 2 electrons. Maximum only there are 2 electrons, right? If you go for the second principal energy level, there are 2 types of sub energy levels, S and P. So in the P sub energy level, there can be 6 electrons. If you go for the third principal energy level, there are 3 sub energy levels, SPD. Number of electrons that can exist in the D sub energy level is 10. For SPDF, 2, 6, 10, and 14. If you go for the fifth principal energy level, you can see that S, P, D, F, G, right? So there are 18 electrons in the G sub energy level, right? So if you count the total number of electrons, you can see that 2, 8, 18, 32, and here we can see 15, 50. So the total number of electrons can be obtained an equation 2n squared. So 2n squared means, right, substitute n value 2 here. 2 into 2 squared, 8 here. 2 into 3 squared, 18. 2 into 4 squared, 32. 2 into 5 squared, 50. Right? So this is a common equation to find out total number of electrons when you know the principal energy level. So this table is representing that how many sub-energy levels are representing, how many sub-energy levels are existing in a particular principal energy level, how the electrons are filled, and total number of electrons. You can see that the number of principal sub-energy levels are equal to the principal energy level number. If you go for the third principal energy level, how many sub-energy levels are there? 3, SPD. If you go for the fifth one, how many sub-energy levels are there? SPD, FG. Fine. Can you understand? This is the way. Right? So this is all about the sub-energy level concept. That's all, very easy. Principal energy levels. Now we can find out the sub-energy levels also, right? Inside an atom, sub-energy levels are also existing. Very easy. Right, okay. Now let's go for the next concept. After finding the sub-energy levels, we can go deeper and let's analyze orbitals, right? Energy levels, sub-energy levels. The next concept is what? Orbitals, right? If you go for the orbitals, look at this one. Orbitals. What does it mean by orbital? Orbital means, right, the place where higher probability of finding an electron, right? A place where higher probability of finding an electron, right? So that is known as orbital. Remember, orbitals are named as actually using the sub-energy level name. Now, for example, if you consider S sub-energy level, or S subshell, right? In the S sub-energy level, there is only one orbital, right? Because we know that the maximum number of electrons in an orbital, the maximum number of electrons in the S sub-energy level is how much? 2, I told you. So therefore, so this is only one and only orbital in the S sub-energy level, and there are 2 electrons. So this is the orbital in the S sub-energy level, right? Normally orbitals are denoted in this way. And if you go for the P sub-energy level, right? If you go for the P sub-energy level, I told you that there are 6 electrons, right? There are 6 electrons. So how that these 6 electrons are existing? Remember, students, there are 3 orbitals are, right? Electrons are filled in this way: 1, 2, 3, 4, 5, 6. Right? So how many orbitals are there? There are 3 orbitals. Ne? There are 3 orbitals. 3 orbitals. If you go for the d sub energy level, how many electrons are there? 10 electrons. There are 10 electrons. Then should tell me how many orbitals should be there. There should be 5 orbitals. 1, 2, 3, 4, 5. Right? I'll tell you, there is a rule that how the electrons are filling to the orbitals. First of all, parallel spin electrons are filling, and then only opposite spin is going to fill. That is known as Hund's rule. 6, 7, 8, 9, 10. That means there are 5 orbitals. Right? So here you can see 5 orbitals are there in the d sub energy level. If you go for the f sub energy level, let's go for the f sub energy level also. If you go for the h sub energy level, you can see that how many electrons are there? 14 electrons are there. If there are 14 electrons, so you should know that how many orbitals are there? 1, 2, 3, 4, 5, 6, 7. So this is the way that how electrons are filling. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So likewise, we can go for the G sub energy level. There are 18 electrons. We can draw 9 orbitals. In the S sub energy level, we have only 1 orbital. And inside orbital, there are 2 electrons. The maximum number of electrons that can exist inside an orbital is 2. And remember, these 2 electrons are rotating to 2 different directions. If one is rotating to clockwise, other one is rotating to counterclockwise. This is known as Pauli's exclusion principle. In other terms, we can say that for 2 electrons in an orbital, they should have 2 different quantum number set. Right? Since we didn't discuss the quantum number set, I'll give you the simple definition for the Pauli's exclusion principle. Pauli's exclusion principle means there can be maximum 2 electrons inside an orbital. So these 2 electrons are rotating to 2 different directions. Their behaviors are 2 different, right? Okay. In S sub energy level, there is only 1 electron. P sub energy level, 3 electrons. D sub energy level, 5 electrons. S sub energy level, 1 orbital. P sub energy level, 3 orbitals. D sub energy level, 5 orbitals. F sub energy levels, 7 orbitals. And you should know how many electrons are existing in the each sub energy level. So this is the orbital concept. Very easy. How we can denote orbitals? When we are denoting orbitals, we are using a circle. So inside an orbital, there can be only 2 electrons. Okay. So that is the way. Right. And in addition to that one, actually, we need to discuss the shape of the orbitals. So mainly we are taking SPD. If you go for the shape of S orbitals, remember shapes, right? S orbital is actually they are telling that it's kind of a spherical shape. Spherical. So this kind of a spherical shape, right? For the p orbital, actually they have given what? Dumbbell shape. What is the shape of a p orbital? Dumbbell, right? Dumbbell shape. Dumbbell shape means it's kind of like this, right? We draw that one in vertical way. This is the way. These are the shapes of p orbitals, dumbbell, right? And I want to remind you that for the D sub energy level, we have different shapes, some kind of a donut shape, donut and dumbbell both are there. So you can search that one, okay? So if you go for the p orbitals, p sub energy level, inside the p sub energy level, there are 3 p orbitals. There are 6 electrons. So these 6 electrons can be located inside 3 b orbitals. Actually, there are 3 orbitals. Actually, these 3 orbitals are existing in this way. So this is very important. Huh? If we consider the plane XYZ, and this is C, so these are 3 planes XYZ, right? So in the X plane, So this is px orbital. Look at this one. The orbital exists in the x-plane is px. And the orbital exists in the y. This is y, right? In the y-axis, this is known as py, right? And the orbital existing in the z plane, that is known as pz, right? Can you see that there are three types? Px orbital, py orbital, and pz orbital, right? So if you draw that one, in the same diagram, it's look like this, right? Y, x, and z. Here the px orbital, and here we have px orbital, py orbital, and this is pz orbital. All right, look at this one. Px, py, pz, right? That's the way. So they are in three different planes. Try to understand. Very easy. This is not in our syllabus, but remember, if I told you that there are 5d orbitals, So the types of these orbitals actually are dxy, dyz, dxz, dz squared, and the last one is dx squared y squared. Okay, so you don't have to remember this one for your knowledge. You can remember these are the 5d orbitals. Go to the Google and search value. What are the shapes of d orbitals? Then you can see the shapes. Okay, so those things are not related to our syllabus. So therefore, we don't have to go that much deep, right? Right. So this is the theories related to the orbitals, right? Very easy. These things are not that much difficult. Okay, very easy. Right. So I'll explain you here the Pauli's exclusion principle also. Pauli's exclusion principle. Remember, Pauli says that there can be maximum 2 electrons in an orbital, and they have opposite spin. In other terms, we can tell that they have two different quantum numbers set. Okay. So our next topic is electron configuration. Very important, right? So remember Pauli's exclusion principle says that there can be maximum 2 electrons in an orbital and they have opposite spin. They have 2 different quantum number sets, right? Okay. Now our next topic is electron configuration. So what does mean by the electron configuration? So electron configuration means what? Easy. You have learned the electron configuration in your oral time, but that's not the correct one. So here actually now we have learned energy levels, sub-energy levels, orbitals. Using them only, we are going to find out the electron configuration. Remember, electron configuration is used to define the exact location of electrons, or else we can define the electrons, the electron system inside an atom using the electron configuration, right? So therefore, this is very important. Let's see. Now, look at this one. If you ask to write down the electron configuration for sodium-like element, let's see, 11. So normally, this is the way you are writing the electron configuration. Okay, very easy. We know that. Let's go for the first principal energy level. So therefore, I will write down here first. What is the sub-energy level that existing in the first principal energy level? Only S. In the first principal energy level, S sub-energy level, how many electrons are there? 2. Therefore, configuration can be written as 1:2. Right? And then, so the first principal energy level is done because there can be maximum 2 electrons. If you go for the second principal energy level, there are 2 sub-energy levels. Those 2 sub-energy levels are 2s and 2p. There are only 2, S and P. In the S sub-energy level, there can be 2 electrons. In the P sub-energy level, there can be 6 electrons. Right? Now, if you go for the third principal energy level, starting in S, in the S sub-energy, there can be maximum 2 electrons. But remember, students, sodium's atomic number is 11. We can stop at here, 1. 1s2, 2s2, 2p6, 3s1. This is the configuration of sodium. Inside the first principal energy level, there is a S sub-energy level. There can be 2 electrons. Inside the second principal energy level, there is a S sub-energy level as well as P sub-energy level. Inside the S sub-energy level, there are 2 electrons. Inside the P sub-energy level, there are 6 electrons. And there is only one remaining electron that is going for the third principal energy level, S sub-energy level. So that's all. If you know the energy level concept, sub-energy level concept, and the orbital, these things are nothing for you. Right? These things are nothing. Let's go for silicon. Right? As an example, silicon. 14. What should be the configuration? 1s2, done with the first principal energy level. 2s2, 2p6. Right? Second principal energy level done. Now 3s2, third principal energy level, S sub energy level also done. Because here 14 electrons are there. 2, 4, 10, 12. Then the remaining electrons are 2p2. The maximum number of electrons we can go for here is what? 2p6. Right? 2p6. Try to understand. Let's go for nitrogen. 7. 1s2, 2s2. Right? 2p3. 2p3. This is nitrogen. First principal energy level, S sub energy level, 2 electrons. First principal energy level, second principal energy level, S sub energy level, 2 electrons, and P is 3. We can go for neon. 1s2, 2s2, 2p6. Right? Aluminium. 1s2, 2s2, 2p6, 3s2, 3p1. 3p1. Argon. 1s2, 2s2, 2p6, 3s2, 3p6. Here's the argon. Potassium. 1s2, 2s2, 2p6, 3s2, 3p6, 3d1. Is this correct? Is this correct? What is the potassium's configuration? Is this correct? No, this is wrong. This is wrong, right? If I write down the calcium configuration 20, 1s2, 2s2, 2p6, 3s2, 3p6, 3d2, is that correct? Is that correct? No. These both configurations are potassium and calcium, both are wrong. Why is that? So this is correct. After P sub energy level, since we are in the third principal energy level, we have to go for the D sub energy level. There can be D sub energy level. Yes, Aufbau. Here is the first theory we are going to learn under the electron configuration. I'm going to explain you why these configurations are. The potassium's exact configuration is 3p6, 4s1, and calcium is 4s2. So how is that possible? After 3p, that should be 3d, right? I think you have made a mistake, sir. No. Actually, this should be the correct configuration. This is correct. This is correct. I'm going to explain you Aufbau principle. Remember, students, electron configuration means how the electrons are filled to the energy level in order, energy level order. But remember, when we are learning the electron configuration, we have to learn many things, right? So the first thing I'm going to teach you here is Aufbau principle, right? The first thing I'm going to teach you here, Aufbau principle. Look at the Aufbau principle. Aufbau is a German term, right? Aufbau meaning that building up something. That's what meant by the Aufbau, building up something, Aufbau. Now, we are expecting that when we are writing the electron configuration, the electron should be filled into the correct order of the energy levels. What should be the correct order? 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. So this is the expected order of filling electrons, isn't it? When we are writing down the electron configuration, this is the order that you expected. But remember, students, this is not correct. This is not the correct order, right? According to the Aufbau principle, we can say, right, look at the order. 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, 5g. Okay. And here I'll write down 6s, 6p, 6d, 6f. So that is enough. Right. Now look at this one. Listen to this very carefully. Right. 1s, 2s, okay, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 5d, 6p. Look at the pattern. What is that pattern? The pattern is, right? The pattern is 1s, 2s, 2p. Okay, that is okay. And then 3s, 3p. After 3p, we are expecting that it should be 3d, but the order is 4s. And then 3d, 4p, 5s, 4d, 5p, 6s. Look at the order. Look at the order. Right? So this is not the expected way, right? Aufbau principle says that this is the way, practically, this is the way that electrons are filling to the energy levels. For downward, energy is increasing. Energy increases. Right? Aufbau principle says that how the electrons are going to fill into the sub-energy levels. Practically. Right? Practically, this is the way that electrons are filling to the sub-energy levels. Remember the order 1s, 2s. Look at this one. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s. That should be the order. Right? This is the electron filling order. Electron filling order. Electron filling order for the elements. Right? This is not the electron configuration. So then how we can write down the electron configuration? Now shall we take that potassium and calcium? One. Potassium was 19, right? Potassium was 19. 1s2, 2s2, 2p6, 3s2, 3p6, right? After 3p, according to the filling order, what it should be? 4s, not 3d. Therefore, we have to write down 4s1. Calcium, which is 20, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. This should be the configuration. So how is that happen? So that is happen because of the energy. I'm going to draw the energy diagram, then you will understand. Look at this one. N equal 1, N equal 2, N equal 3, N equal 4, and N equal 5. Right? So these are the sub-energy levels. In the first principal energy level, we have only 1s. If you go for the second principal energy level, we have 2s and 2p. Right? So this axis is energy. Right? This axis is energy. And here, this one is considered as 3s, 3p, 3d. That means 3s, 3p, and this is 3d. Look at this one. If you go for the 4d, 4d come down after 3d. Look at this one with you. Energy of the 4s orbital is lesser than the energy of 3d orbital. That's why 4s electrons are filling. Electrons are filling to the 4s orbital, 4s sub-energy level before 3d. That is the reason. And here we can say that after 4s, 3d, and then 5, 4p. Right? After 4p, before it go for the 4d, it comes to the 5s. Here, look at this. This is 5s. And then only it is going for the, right? So this is some kind of a weird pattern, because we know that these sub-energy levels are mixing. Right? When the energy increases, we know that energy level gap is decreasing. When the energy level gap is decreasing, these orbitals can mix. That means gap is reduced. Gap is reduced. So therefore, these electrons can jump here and there easily because energy gap is very low. Look at this one. An electron can't jump easily from the first principal energy level to the second principal because gap is very high. But if you go for the fourth one, fifth one, sixth one, likewise, consecutive energy levels, these electrons can be shifted here and there. So therefore, try to understand this is the reason why we have this kind of a variation. Aufbau principle explains that how the electrons are filling to the energy levels, sub-energy levels, right? So this is the energy diagram of these sub-energy levels. Try to understand. Okay, very, very important. Right. So that is very important theory under the electron configuration. Right. Now look at the next theory part. Hund's rule. So what does mean by the Hund's rule? Remember, Hund's rule says that when the electrons are filling to the orbital, they are following that electrons are filling to the orbitals one by one. Just imagine P sub energy level. Let's go for the P sub energy level. If you go for the P sub energy level, there are 3 P orbitals in this way. Electrons are filling to the P sub energy level one by one. So that's what Hund's rule says that. So the first electron is filling to the first orbital with the same direction, and the second electron also filling to the orbital with the same direction. Third electron is also filling to the orbital in the same direction. And this is fourth one. Now look at this one. Look at the fourth electron. The fourth electron is going for the again first orbital, and this is opposite in the direction. And if you go for the fifth electron, opposite in direction. And now this is in this way. Remember, this is P1, P2 configuration, P3 configuration, P4 configuration, P5 configuration, and P6. Remember, students, P3 configuration is considered as stable configuration, and P6 is also considered as a P stable configuration. Why? What is the reason? The reason is, look at this one, the symmetrical order arrangement, the symmetrical arrangement of the electrons. Because of the symmetrical arrangement of this electron, we consider this configuration, P3 configuration, is to be stable. As well as P6, all the orbitals are completely filled, right? So therefore, these configurations are, so this configuration is very much stable than this P3, right? So try to understand, Hund's rule says that when the electrons are filling to the orbitals, electrons are filling one by one with the same direction. And then only opposite direction electrons are filling. And the next thing you have to remember here, apart from the Hund's rule, we can say that If you analyze these configurations, P3 and P6 configurations are stable because of the symmetrical arrangement. Among them, P6 is the most stable one, right? If you go for the D sub-energy level, D sub-energy level, there are 5 D orbitals. In this way. One by one, Hund's rule. One by one, means same direction. Right. D1 configuration, D2 configuration, D3, D4, and D5. You can see that D5 configuration is stable. Then D6, D7, D8, D9, and this is D10. D10 configuration is the most stable one among the others, right? D5 and DT configuration are stable, as well as P3 and P6 also. Those are also stable, right? Try to understand, okay? This is very important. Now look at this one. Let's write down some configuration for elements. Scandium 21. Electron filling order according to the Aufbau principle. Electron filling order, that is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. This is the electron filling order according to the Aufbau principle. But remember, students, this is not the configuration. Electron configuration means we have to rearrange that one according to the energy level order. 1s2, 2s2, 2p6, 3s2, 3p6, 3d1, 4s2. This is the electron configuration. Try to understand the difference between electron configuration and the electron filling order. As the next element, I'll consider chromium. Electron filling order. Electron filling order is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. Yes. And the electron configuration is very important. Why? What is the reason? The reason is actually, you can see that, now look at the electron configuration. This is very important. 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, 4s1. Why 3d5 and 4s1? Remember, students, here this is the S sub-energy level, and here we have d5 orbitals. In order to gain the greater stability, one electron will be shifted to the d sub-energy level in the chromium atom. And then the configuration is becoming 4s1 and 3d5. 4s1 and 3d5 stable, therefore the configuration of chromium is 3d5, 4s1. It's rearranging. Chromium's configuration is rearranging. In the 3D elements in the periodic table, we are considering chromium and copper are the elements that rearrange in their electron configuration, right? As the third example, let's go for the manganese. Manganese is 25. electron filling order 2p6, 3s2, 3p6, 4s2, 3d5, right? So this one electron configuration is 3d5, 4s2. Easy. As the fourth example, let's go for the copper 29. This is 4s2, 3d9. Again, this configuration is rearranging. Why? Because we know that 4s2, 3d9. It should be like this. 4s2, 3d9 is look like this. So we can rearrange this electron configuration to 4s1 and 3d10 by giving one electron there. So therefore, the configuration is becoming stable by rearranging the configuration 3d10. Number 5, zinc. Zinc is 30. Electron filling order 4s2, 3d10, and this is 3d10, 4s2. Very easy. So this is the electron filling order and the electron configuration. Try to understand. Now, okay, sorry, mic is muted. Right, okay. So our next topic is quantum numbers. Can you hear me properly? Done. So there are 4 types of quantum numbers: N, L, M, L, MS. Remember, simple N means principal quantum number. Principal quantum number. Principal quantum number is representing the principal energy level. Principal energy level. So that is known as the principal quantum number. Simple L, this is known as angular momentum. Angular momentum or azimuthal quantum number. So this is representing actually the sub energy level. So this is like our address, right? House number, street number, village, and city, right? So likewise here only energy level, sub energy level, ML. ML means magnetic quantum number. Magnetic quantum number is representing what? Number is representing the orbital type. Orbital type. Right? And the last one is spin quantum number. Spin quantum number. Right? Spin quantum number is representing the rotation of the electron. If not, what is the electron? There are 2 types. Rotation of the electron. Right? So there are 4 types of quantum numbers: NL, ML, MS. Principal quantum number, which is representing the principal energy level. Angular momentum quantum number, which is representing the sum energy level. Magnetic quantum number representing the orbital type. Spin quantum number, which is representing the rotation of electron. Right? So that's really easy. Now, if we go for the principal quantum number N, remember students, principal quantum number N. So the principal quantum numbers, we can assign the values N equal 1, 2, 3, 4. Likewise, we can go for the until nth energy level. So the values that we are assigning for the principal quantum number is 1, 2, 3, 4 like this. So the next one is azimuthal quantum number, which is represented the sub energy level. For the sub energy levels, we are giving quantum numbers like this: sub energy level, and here we can consider the quantum number, azimuthal quantum number, right? S, P, D, F. For the S, we are assigning 0, P1, D2, and F is 3. So these are the quantum numbers we are assigning for the sub energy levels. For the sub energy level 0, P sub energy level 1, D sub energy level is 2, F sub energy level is 3. I'll explain you, right? When we are discussing the examples, I'll explain you. If you go for the magnetic quantum number, this is really interesting, right? The reason is, if you go for the S sub energy level, there is only one orbital. For that orbital, we are giving, there are 2 electrons, quantum number 0. That is what? Magnetic quantum number. If you go for the P sub energy level, there are 3 p orbitals. For them, we are giving quantum numbers -1, 0, +1. Right? If you go for the D sub energy level, there are 5 d orbitals. Look at the magnetic quantum number: 0, middle one, this one -1, -2, this is +1, +2. Right? If you go for the F there are 7 orbitals. 1, 2, 3, 4, 5, 6, 7. For this one, 0, plus 1, plus 2, plus 3. And here minus 1, minus 2, minus 3. Right? So these are the magnetic quantum numbers we can assign. Right? And the last one is spin quantum number. Spin quantum number is really easy. If there are 2 electrons in an orbital, we can assign plus half for this electron and minus half for this. That means if one is rotating to clockwise, other one is counterclockwise. If this is counterclockwise, this is clockwise. So this is the summary of the quantum numbers. Very easy. Very easy. Okay. Look at the magnetic quantum number. Most of the students are confusing with this magnetic quantum. That is very easy. Magnetic quantum number is orbital type. If you go for the S sub energy level, we have only one S orbital, so there was 0. If you go for the P sub energy level, there are 3 orbital types: minus 1, 0, plus 1. If you go for the D sub energy level, 5 D orbital types: minus 2, minus 1, 0, plus 1, plus 2. If you go for the F, minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. Energy level, sub energy level, orbital type, and the spin. Plus half or minus half. Right? That's very easy. Right. Let's consider an example. I'm going to consider neon, and I'm going to write down quantum number set for the all electrons in neon. Remember, neon is 1s2, 2s2, 2p6. This is the configuration. We know that if you go for the first principal energy level, there is an orbital. There are 2 electrons. If you go for the second principal energy level, here we have s orbital, 2 electrons, and here we have 3 p orbitals. And there are 6 electrons. Right? Now we have to write down the quantum number set for. There are 10 electrons. Right. Now let's choose this electron. Okay. So we can write down quantum number set for this one. Right. 1. First principal energy level. S sub energy level 0. Right. S orbital 0. Let me consider this is plus half. Here the quantum number set. So quantum number set is kind of an identification number for particular element. Quantum number set for an element is unique. Remember. So the other electron, right? Other electrons, I'll give you the numbers for this one. 1, 2. And this is number 1. This is number 2. 1, 0, 0, minus half. Right? S sub S principal, first principal energy level, S sub energy level, S orbital, plus half or minus half. We are done with these 2 electrons, right? Now let's go for this one. Let me consider this is third one, and this is fourth one, right? Third electron, that is belong to the second principal energy level, S subenergy level, therefore 0, S orbital 0, plus half, other one is minus half. Very easy, right? Very easy. Okay. Let me consider this electron is the fifth one, this electron is the sixth one, and this is the seventh one, right? 5, 6, 7. 5. Second principal energy level, P sub energy level, therefore 1. Right? Which orbital is this? We can assign this is minus 1, this is 0, plus 1. Therefore, minus. Let's consider this is plus half. Then the sixth one, second principal energy level, right? P sub energy level 0, orbital plus half. Seventh electron, second principal energy level, P sub energy level plus 1 orbital and the plus half. Right? And let me consider this is 8th electron, this is 9th one, and this is 10th one. 8, 9, 10. Right? 2 second principal energy level, P sub energy level, minus 1 minus half. Second principal energy level, P sub energy level, 0th orbital minus half. Plus 1 minus half. Look at the way. Each and every electron has a unique quantum number set. That's all. This is the concept. If you can understand the concept, you can do any kind of a question. Very easy.
අදන් නෝට්ටු වෙනද ඉංගෝලිප
Okay, right. We have remaining only one part, classification of elements and the periodic trends, that means atomic properties. Let's have another break, okay? 10 minutes break, and let's discuss the remaining session. Third session, the last session, after the break, okay? Take a break quickly. Right, okay. Shall I start the remaining parts? Now we can discuss about the periodic table. I'm not going to draw the periodic table, right? So let's analyze the periodic table, right? In the periodic table, actually, what are the things we have to remember, right? In the periodic table, the first thing you have to remember, there are 18 elements. First of all, who built the periodic table? Can you remember? We learned that. Some names are there to remember. Dmitri Mendeleev, Lothar Meyer. So those are the famous names. So I'll write down the names that are very important, right? Johann Wolfgang, right? And then we can John Newlands, right? Lothar Meyer and Dmitri Mendeleev. Mendeleev. Okay. So we consider that the current periodic table is developed by Dmitri Mendeleev. And remember, there are 118 elements in the periodic table. And the periodic table is classified blockwise, right? Actually, there are 4 blocks in the periodic table: S block, P block, T, and F blocks. These are the blocks in the periodic table. Especially, I want to mention you about here F block. F block is actually categorized as 2 series in the periodic table. First one is lanthanide series, and the next one is actinide series. Lanthanum series and the actinide series. Right? Try to understand. And if you analyze further the periodic table, how many periods and how many groups are there? Can I remember that we discussed? In the periodic table, there are 7 periods, right? There are 7 periods, and there are 18 groups in the periodic table. 7 periods and 18 groups in the periodic table, right? And then remember, so period means actually rows in the periodic table. Group means columns in the periodic table. 7 periods and 18 groups in the periodic table, right? And then what else we have to discuss on the periodic table? We know that there are 11 gases in the periodic table. Can we name them element wise? Hydrogen, helium, right? Nitrogen, oxygen, fluorine, neon, right? Chlorine, argon, krypton, xenon, radon, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So these are the 11 gases in the periodic table. And remember, in the periodic table, there are 2 liquids, right? In the standard state, there are 2 liquids. First one is bromine, and the next one is mercury. Bromine and mercury are the 2 liquids in the periodic table that we can consider, right? Try to understand these things are Very, very important. Right? Very important. Okay. And then we can classify the elements in the periodic table, right? Elements in the periodic table that metals and non-metals. Most of the periodic table elements are metals. That means if you consider, right, 80%, right, approximately 80% of the periodic table are metals. So the remaining are non-metals. Okay, 80% are metals. If you consider the metalloids, what does mean by the metalloids? Metalloids means the elements which are having metal and non-metal properties, right? So what are the metalloids in the periodic table? Right? So the metalloids are boron, silicon, germanium, arsenic, antimony, tellurium, astatine, and polonium. So these are the metalloids. Metalloids means elements which are having both metal and non-metallic properties, right? Both non-metallic properties, metals and non-metallic properties. And then amphoteric elements. What does it mean by amphoteric elements? Amphoteric elements means elements which can react with acids and bases, both. Beryllium, right? Then aluminium, tin, lead, and zinc. So these are the 5 amphoteric elements in the periodic table, right? These are the 5 amphoteric elements in the periodic table. You heard me, right? This is very important. You have to remember these things under the periodic elements, okay? Periodic table. This is not all about drawing the periodic table or memorizing the periodic table. You have to analyze the periodic table, right? Okay. Right. Right. So these are the amphoteric elements. So in the periodic table, they have given some names for group wise elements, right? So if you consider group 1 elements, right? Group 1. In the periodic table, group 1 elements are known as alkali metals. Alkali metals. What are the alkali metals? Lithium, sodium, potassium, rubidium, cesium, francium. So these are alkali metals. Alkali means some kind of basic properties, right? Then group 2. Alkaline earth metals. Alkaline earth metals, beryllium, magnesium, calcium, strontium, barium, radium. So these are alkaline earth metals, right? If you go for the group number 14 elements, they are known as coinage metals. Coinage metals. Coinage metals are copper, silver, and gold. These are coinage metals. right? Group number 16 elements are chalcogens. Chalcogens means what? Group number 16 elements: oxygen, sulfur, selenium, tellurium, polonium. So these are the chalcogens, right? And then group number 17, this is halogens. Halogens: fluorine, chlorine, bromine, iodine, and astatine. And group number 18 elements are known as noble gases, or else they consider rare gases, right? Neon, argon, krypton, xenon, radon. So these are rare gases. Okay. Sorry, this is group number 11. Okay. Sorry. Yes. Okay. Good. Very good. Group number 11. Okay. And remember, in the periodic table, the only group that existing all three states of matter is group number 17, right? Group number 17 elements, group number 17 contains all three states of matter: solid, liquid, and gases, right? Because fluorine and chlorine, both of them are gases. Bromine is a liquid. Iodine at the standard state, that's a solid. Astatine also solid. So therefore, group 17 contains all three states of matter, right? Right. If you consider, period wise elements, period and 4 and 6 contain all three states of matter. Okay, because bromine and mercury is there. Since bromine and mercury is there, period number 4 and 6 contain all three states of matter. Remember. So these are the main things you have to remember under the periodic table. Right, okay. So the last topic of the first unit is what? Atomic properties. Right. Under the atomic properties, we are going to discuss about 4 atomic properties. Right. So the number 1 is radius. Atomic radius. So the second one is what? First ionization energy. And the third one is electron gain energy. And the last one is electronegativity. Number 4 is electronegativity. So these are the 4 atomic properties we have to discuss. Atomic radius, first as energy, electron gain energy, and the electronegativity. If we go for the atomic radius, let's go one by one. In order to measure the radius of atom, there are 3 methods. There are 3 main methods. Right? Number 1 is covalent radius. Number 2 is Van der Waals radius. Van der Waals radius. Number 3 is metallic radius. Metallic radius. Right? Let's go one by one. What does mean by the covalent radius? Covalent radius. If we go for the covalent radius, right? Look at this one. Covalent radius means when 2 atoms are combined through a covalent bond. So these are 2 nuclei. When these 2 atoms are combined with covalent bond, right? We are taking the measurement between 2 nuclei. This is D, right? So the radius, we can consider that radius of that atom. We consider this one as covalent radius. Covalent radius means RC. This is equal to D over 2. So you may wonder that if we take the half of this distance, this is not the exact radius, right? Exact radius of atom means what? The distance between the nucleus and the valence shell electron. So this is the valence shell, right? If we assume that atom is look like a sphere, so the exact radius is larger than the covalent radius. But what to do? Experimentally, so this is the accurate method that we can follow, right? So you have to understand that covalent radius is not exactly equal to the exact radius. Covalent radius is lesser than the exact radius. But anyhow, in order to measure the radius of elements, we are using covalent radius, right? Covalent radius is not equal to the exact radius. Covalent radius is lesser than the exact radius. When they are forming covalent bond, we are taking the distance between 2 nuclei, and half of the distance is considered as the radius. Got it? Normally, covalent radius is measured for the elements who are forming covalent bonds. For example, hydrogen covalent radius. Hydrogen atoms are connecting. Chlorine is forming to chlorine another atom. So that is also a way of finding the covalent radius, right? Right. The second method we can go here is what? Van der Waals radius. Van der Waals radius. Van der Waals radius means when the 2 atoms are very close to each other, they are not forming chemical bonds. The reason is actually they cannot form the chemical bonds. When they are not forming chemical bonds, we are taking the internuclear distance, right? So this is D. So the radius, this is known as Van der Waals radius. Van der Waals radius is denoted by RV. This is equal to D over 2, right? Again, so this is not the exact radius, right? What to do, right? Some of the elements like helium, neon, they are not forming chemical bonds. So there should be a method to find out the radius. So therefore, we are taking the measurement when the two atoms are very close to each other and we take the half of the distance. So that is known as van der Waals radius. Remember, van der Waals radius is greater than the exact radius of the atom. We are taking some measurements for the radius, but those are not the exact values, right? So look at these two methods. Actually, these two methods are not 100% accurate. Covalent radius is lesser than the exact radius. Van der Waals radius is greater than the exact radius. So how we can say that they are accurate, okay? 100% accurate. But practically, these are the ways of finding the radius. We don't have any other methods. Let's go for the next method, metallic radius. Metallic radius is somewhat acceptable than these two methods because accuracy is very high in metallic radius. The thing in metallic radius is in the metallic radius, the atoms are very close to each other, right? These are the metal atoms, right? Now look at the distance, internuclear distance d, and we are taking the half of that one. So that is accurate. If you take the metallic radius Rm, that is d over 2 again here. So that is exactly equal to the exact radius. No issue, right? According to the diagrams, you can understand, right? Exact radius is equal to the metallic radius, no issue. Right? Exact radius equal to the metallic radius. So among the three methods, which one is more accurate, right? We know that exact radius is always equal to the metallic radius. So this is greater than the covalent radius, lesser than the van der Waals radius. So Rm, metallic radius, is the most accurate radius we can take, right? So this is the three types of radius that we have to learn. Right. Okay. Now, look at this. We are going to discuss factors affecting to atomic radius. What are the factors affecting to the atomic radius? Remember, there are two factors affecting to the atomic radius. Number one is shielding effect. Number two is nuclear charge. Shielding effect and the nuclear charge are the two factors affecting the radius, right? Remember, shielding effect means You know, shield means what? Shield means protector, kind of a protector. If you consider an atom, right? So this is an atom. So this is the valence shell electron, right? And these are the inner shell electrons. These inner shell electrons are known as co-electrons. Remember, students, atomic nucleus is positively charged and this electron is negatively charged. This electron is attracted towards the atomic nucleus, right? This electron is attracted towards the nucleus. But remember, these co-electrons, right? These blue color electrons are known as co-electrons. Inner shell electrons are known as co-electrons. These electrons are protecting this electron, valence shell electrons. Co-electrons are protecting the valence shell electrons in order to reduce the nuclear attraction force felt by this electron. Can you understand? Remember, this nuclear attraction force reduced by the number of co-electrons inside the atom. So that is known as shielding effect, right? So shield means kind of an army that is protecting this electron from the nuclear attraction force. We know that if it is attracted to the nucleus, the size of the atom is reducing. That means when the strength of the co-electrons are increasing, atomic radius is increasing. If not, radius is decreasing. So we consider that shielding effect, right? How that shielding effect is affecting to the atomic radius. Atomic radius is directly proportional to the shielding effect. Shielding effect, right? When shielding effect increases, definitely atomic radius increases, right? Shielding effect is actually denoted by S. How we can measure the shielding effect? By counting the number of co-electrons. Shall we consider an example? Sodium and magnesium. Look at this. Not sodium and magnesium. Let's take lithium and sodium. What is the shielding effect of lithium? We know that lithium's electron configuration is 1s to 2s1. So this is the valence shell electron, right? This is the valence shell electron. So therefore, 1s2 is the shielding effect of lithium. That means 2 electrons are there, right? So that is the shielding effect. Sodium, 11. Electron configuration is 1s2, 2s2, 2p6, 3s1. This is the valence shell electron, last electron. And other electrons are considered as co-electrons. So therefore, co-electrons is the measurement of the shielding effect. So therefore, 10 electrons, right? So when the shielding effect is very high, atomic radius is increasing. That's correct, because we know that lithium, sodium, potassium, rubidium, cesium, down to the group atomic radius are increasing, right? Because shielding effect is increasing. Can you understand? So this is shielding effect. Atomic radius, try to understand how that shielding effect is affecting the atomic radius. When shielding effect increases, atomic radius is increasing, right? The second factor we have to discuss is the nuclear charge, right? Nuclear charge. Let's see how that nuclear charge is affecting to the radius. Nuclear charge denoted by Z. Nuclear charge is denoted by Z. Remember, nuclear charge means nothing else, number of protons. Number of protons. Nothing else, number of protons. Right? So how that nuclear charge affecting to the radius? Let's compare sodium and magnesium. Look at this one, students. So sodium's nuclear charge is 11, magnesium's nuclear charge is 12, plus 11 and plus 12. Remember, when the number of protons are high in the nucleus, what will happen to the radius? Radius is gonna reduce. Neither. So all of the electrons are attracted towards the atomic nucleus. So therefore, when the nuclear power is very high, that means the attraction power of the nucleus is very high. What will happen to the radius? Radius is reducing. So therefore, we can always consider that magnesium has the least radius than sodium. Therefore, you can understand that how is that nuclear charge is affecting to the radius. Nuclear charge is inversely proportional to the radius, which means when nuclear charge decreases, only atomic radius will increase. Try to understand. They are inversely proportional, right? They are inversely proportional. So shielding effect means number of co-electrons which are protecting the valence shell electrons. When the shielding effect is very high, radius is increasing. Nuclear charge means number of protons. When the number of protons or the nuclear charge increasing, atomic radius will reduce. So they are inverse proportional, right? Therefore, we can consider that together. Together, I can show you that. Atomic radius is directly proportional to the shielding effect and inversely proportional to the nuclear charge. So this is the relationship you have to remember. Okay. And one more thing I want to remind you, effective nuclear charge, ZEFF. Effective nuclear charge. Effective nuclear charge is represented, is used to, without considering these two factors separately, we can directly take effective nuclear charge, right? Effective nuclear charge is equal to nuclear charge minus shielding effect. Minus shielding effect, right? As an equation, we can tell that ZEFF is equal to Z minus S. So this is the effective nuclear charge. So effective nuclear charge means a combination of these two factors, nuclear charge and shielding effect. Combination of two factors. Okay. Effective nuclear charge means combination of two factors, nuclear charge and the shielding effect. So how we can make the relationship between the effective nuclear charge and the radius? Very easy. Effective nuclear charge is also same as nuclear charge. Without considering these two factors separately, we can consider them together and tell that when the effective nuclear charge decreases, what will happen to the radius? Radius increases. Okay, so that's what you need to understand here. Try to understand. Okay, very, very important. Right. Okay. Remember, students, down to the group, down to the group, atomic radius increases. Down to the group, atomic radius increases. Right. Along a period, what will happen? Atomic radius is decreasing. Right. Along a period, from left to right, atomic radius decreases. Okay. So you can apply the theories you have learned, nuclear charge and shielding effect, effective nuclear charge, everything. And you can derive that one, okay? So you can, if you want, you can calculate the effective nuclear charge. For example, I'll take lithium and beryllium. For the lithium effective nuclear charge is 3, number of coelectrons are 2, therefore plus 1. For beryllium, effective nuclear charge can be calculated 4 minus 2, that is plus 2. So who has the highest effective nuclear charge? Beryllium. So therefore, beryllium has the least radius. Lithium has the highest radius. So likewise, we can apply. So down to the group, we cannot apply the effective nuclear charge. They are actually the dominant factor will be energy levels. Down to the group, we know that number of energy levels are increasing. So therefore, radius is increasing. Okay. Right. And the next thing you have to remember, if you consider an element with the cation, element and its cation, who has the highest radius always? Sodium and sodium plus, who has the highest radius? Definitely sodium, because it's removing electron. So therefore, sodium has the highest radius. If we consider an element and it's anion, who has the highest radius? Chlorine and Cl minus. Definitely, it's the anion because it's gaining electrons. So therefore, it has the highest radius. Okay. Right. So our next topic is first ionization energy. First ionization energy means I1. I told you what does mean with ionization energy. Here mainly we are talking about how the ionization energy varies. Okay. There are two factors affecting to the ionization energy. Number one is radius. And number two is electron configuration. Atomic radius and the electron configuration, right? So when you consider the ionization energy group wise, right, down to the group, what will happen? We know that down to the group atomic radius is increasing. Atomic radius increases down to the group. When atomic radius increases, ionization energy I1, first ionization energy, decreases, right? The reason is here electron configuration won't dominate when we take in the ionization energy. The reason is if you consider group wise, just imagine lithium, sodium, potassium, rubidium. Their valence configurations are same S1. So this is 2s1, 3s1, 4s1, 5s1. Their valence configurations are similar, right? So therefore, in electron configuration won't dominate here. Only the radius. Since the size is increasing, we can easily remove one electron from the atom. So therefore, atomic radius increases, therefore ionization energy decreases. Very easy. So group wise, we can compare the ionization energy in this way. So the issue is with the what? Period wise elements. That's the issue here. Let's see. Right. Let's see what will happen with the period wise elements. So for the period wise elements, we know that actually atomic radius is decreasing along a period. Along a period, atomic radius is decreasing. So that we are expecting ionization energy should be what? Increasing in this way. We can, if you draw the graph, we are expecting that ionization energy of the elements, right? Let's consider lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. We are expecting that ionization energy should increase gradually in this way. Because atomic radius is decreasing. When the atomic radius decreases, ionization energy is increasing. Because we need to supply a lot of energy to remove electrons from the atom. But remember, this is not the variation. This is the expected variation. Okay. Along the period, this is not the correct variation. Group wise, we can directly tell this is the way that ionization energy varies. But period wise, we can't tell that. Right. So I'm going to draw the ionization energy graph. Then you will understand how that elements ionization energy is depending on the electron configuration. Look at this one. This is very important. Highest ionization energy belongs to the helium because it has the stable configuration as well as the least radius. You have to remember this variation. Huh? a zigzag variation, right? In this, right? Look at the graph, what you can see in the graph. Right? This is helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, potassium, and calcium. Right? So according to the resource book, hydrogen and oxygen, both of them are in the same horizontal plane. Therefore, let me consider hydrogen is here. This is hydrogen. Right? So you can see that some exceptional behavior shown by beryllium, nitrogen, magnesium, phosphorus. Normally, the typical variation that we are expecting ionization energy along a period that should increase gradually. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, gradually it should increase. In here also, we are expecting that sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon. We are expecting that they should gradually increase. Expected variations along the period since the atomic radius is decreasing, we are expecting these kind of two variations, but that's not the case. We can see some exceptional behavior in beryllium nitrogen, in magnesium phosphorus. Why is that? We know that beryllium has somewhat stable configuration. Beryllium 1s2, 2s2. All the orbitals are completely filled with the electrons, so therefore stable. Nitrogen 1s2, 2s2, 2p3, that is half stable. Then if you consider magnesium 1s2, 2s2, 2p6, 3s2, that is also stable. Phosphorus 1s2, 2s2, 2p6, 3s2, 3p3, that is also somewhat stable. These configurations are somewhat stable. So that's why we are having some exceptional behaviors in the ionization energy. Right? Stable configurations. So this is the way that electron configuration is affecting to the ionization energies along a period. Try to understand. Okay? Very easy. Right? Okay, never. So this is known as a zigzag variation, right? Ionization energy zigzag variation. Very, very important. So this is the first ionization energy graph. You have to remember. In the examination, if you ask to find out the second ionization energy, third ionization energy graphs, or any questions they have given related to the second ionization energy or the third ionization energy, you should be able to derive that one also, because that is really easy, not difficult. How? We know that, students, according to this graph, if I consider the first ionization energy, second ionization energy, and the third ionization energy, right? Highest in which group? And the lowest in which group? So using that, actually, you can identify that. First ionization energy is always highest in, the highest element is helium. We know that one because the least radius, the smallest radius, and the stable configuration, right? So therefore, we can consider that the highest first ionization energy belong to the group number 18 elements. Lowest first ionization energy always belong to the group number 1 elements. Lithium, sodium, potassium, look at them. They always at below, right? So therefore, the lowest first ionization energy belong to the group number 1 elements. If you go for the second ionization energy, so you have to shift these graphs. You have to shift this graph to the left-hand side. Then lithium will come here and beryllium will come here. Because second ionization of lithium means you are removing 1 electron of lithium. After removing 1 electron from lithium, now it's look like what? Helium. Now you are trying to remove an electron from helium. Is that possible? No, that's very difficult. So therefore, the highest in group number 1, lowest in group number 2. Third ionization energy, highest in group 2, lowest in group 13. So likewise, you should be able to derive the second and third ionization energies as well. Got it? That's the way. Right. So that is all about the ionization energy you have to know. So those things are also very important. Okay. Right. Now let's go for the electron gain energy. Now let's go for the electron gain energy. The next atomic property is electron gain energy. Electron gain energy is denoted by Eg, right? So the electron gain energy, first of all, we can define the first electron gain energy, right? How we can define that one? Very easy. So same as in the ionization energy, we are considering gaseous state element. It's gaining 1 electron to form X minus gaseous state anion, right? So the energy associated with this one is known as first electron gain energy, right? Yeah, we didn't do this part. I have to provide you a recording, but doesn't matter. We can just go through these things, okay? These things are very easy. Electron gain energy means the minimum energy. That means the energy associated with gaining electron. Okay, so this X atom has gained 1 electron. So the energy associated with that is known as first electron gain energy, right? First electron gain energy. So remember, most of the time the electron gain energy is actually a negative value, right? Negative value. for the some elements, for the few elements, no need. Don't write anything in the tutorial. So for that one, I'll give you the separate recording. So therefore, don't worry. So now just listen, will you? Right? This is kind of a revision, right? So don't write anything. Just listen, right? Most of the time, electron gain energy is negative value, right? Electron gain energy is a negative value. That means exothermic, right? Exothermic. Exothermic means they are releasing energy. Exothermic means releasing energy. Releasing energy, therefore negative. Okay. In energetics unit, we are going to learn this on unit number 5. Endothermic. Endothermic means they are absorbing the energy. They are absorbing energy. So that is positive. Huh? Positive. So most of the time, this electron gain energy is actually what? Exothermic. They are not the endothermic, exothermic, right? Some endothermic values also there, right? I'll consider some examples, then you will understand. Look at this one. Example, chlorine. Chlorine's electron gain energy value is minus 349 kilojoules per mole. That's an exothermic. So this is the highest value, right? That means the highest electron gain energy value is belong to chlorine, right? Always remember that one. And remember, for beryllium-like elements, look at this one. Beryllium has gained 1 electron, is forming beryllium minus. This is positive, 340 kilojoules per mole, right? Look at this one. That means in order to give 1 electron for the beryllium, we have to supply energy. That is difficult, right? Positive means we have to do a work. Negative means it release the energy. Positive means we have to supply energy. Absorb the energy means that means we have to supply. Understood? So therefore, beryllium, remember these 3 elements, beryllium, nitrogen, and magnesium. They have always positive electron gain energy values. Positive electron gain energy values. Okay? They have always positive electron gain energy values. Remember. Try to understand. Beryllium, nitrogen, and magnesium always having positive electron gain energy values. Positive electron gain energy values. If they have negative values, we consider that one as exothermic, right? Releasing energy. If it is a positive value, we consider that one as endothermic, absorbing the energy, right? Okay. Remember, students, always, second electron gain energy, that means Eg2 is a positive value. The reason is, just imagine X minus gas gaining 1 electron as forming X2 minus. This is always, Eg2 is always greater than 0. The reason is, after gaining 1 electron, this is negatively charged. For the negatively charged one, you are trying to give another electron. Will it accept or repel? Electron, repulsion force will create neither. Right? After giving 1 electron, this is negatively charged. For this negatively charged electron, you are trying to give another electron. Is that possible? No. Right? It's not possible. So therefore, try to understand. This is what? Positive value. Second electron gain energy is always a positive value. Okay. So that is all about, you have to remember regarding the electron gain energy. right? So the last topic of the unit is what? Electronegativity. Very, very important. Huh? Electronegativity is very, very important. Even though that is the last topic, that is very important because this is affecting to the other two units also. Second unit and third unit. Electronegativity. What does mean by the electronegativity? Remember students, electronegativity means, just imagine hydrogen and chlorine has formed a bond, right? So one of the electrons will pull the electrons, these bonding electrons, toward itself because of the ability. So kind of an ability to pull the electron, right? Actually here the most electronegative atom is chlorine. Chlorine is pulling the electrons from hydrogen. That means these bonding electron pairs are attracted towards the chlorine atom. So that ability, that capability is known as what? Electronegativity. Electronegativity means what? The ability to pull the electrons, bonding electron pairs from a bond to itself is known as what? Electronegativity. Okay. So this is very important concept. You have to remember when you go for the second unit and third unit, structure and bonding and the chemical calculation, right? So what is the definition for the electronegativity? Ability to attract the bonding electron pairs when they are connected to each other, when it is connected to another element, right? So in order to measure the electronegativity, there was a scientist known as Linus Pauling, right? Linus Pauling has introduced a scale to measure this electronegativity. That is known as Pauling scale. Pauling scale. According to the Pauling scale, the most, that means the highest electronegative atom in the periodic table is fluorine, F, right? So when an element is connected, may combine to the fluorine atom, right? Remember, fluorine will pull the electrons, right? According to the Pauling scale, these are the values they have given. Hydrogen, lithium, sodium, potassium, rubidium, cesium, beryllium, magnesium, calcium, strontium, barium, boron, aluminium, gallium, indium, thallium, carbon, silicon, germanium, tin, lead, nitrogen, phosphorus, arsenic, what? Antimony, bismuth, oxygen, sulfur, selenium, tellurium, polonium, fluorine, chlorine, bromine, iodine, astatine. For the noble gases, actually, we do not consider the electronegativity values because they are not forming chemical bonds, right? Electronegativity of hydrogen is 2.1. Lithium is 1.0. Sodium is 0.9. Potassium is 0.8. Rubidium is 0.8. Cesium is 0.7. Beryllium 1.5. Magnesium 1.2. Calcium 1.0. Barium is 0.9. So boron is 2.0, 2.5, 3.0, 3.5, 4.0, right? And this is 1.5, 1.8, 2.1, and this is 2.5, 3.0. We are going to discuss a short method for this one. Don't worry, in the paper class, we are going to discuss to remember a short method to remember this one. For now, let's analyze the values, how they are behaving, okay? So the highest electronegative element in the periodic table is what? Fluorine. That means fluorine will pull the electrons, bonding electron pairs in a bond than the others. And the second highest one is oxygen. Third highest one is nitrogen and chlorine. But remember exactly, even though they have given 3.0, 3.0 here, if you go for the second decimal point is highest in chlorine. And that means chlorine has the highest electronegativity. But according to the Pauling scale, they are same. Right? And you can see that some elements have similar values. For example, look at silicon, germanium, tin. They have similar values. Hydrogen, phosphorus, they have similar values. There are so many elements having the similar values. Right? Can we analyze how that electronegativity varying along a period? Along the period, electronegativity is increasing. We can see that. And down to the group, electronegativity is decreasing. So therefore, actually, these elements actually are having high electronegativity values than the others. Right. Okay, so this is the whole theory part that we have to discuss in the first bit. I think I have discussed all the things. I didn't miss anything. I discussed all the theory parts. Okay. So, can you all hear me now? Can you hear me? So this is all about the theories. How the session? So was it useful? We started the 6 and now time is 11 again. So 5 hours. That's very difficult to discuss all the theories of the first unit. You know what is the weight of the first unit, right? I think we discussed a lot of theories. So how about the session? Was it useful for you or not? Or no? Okay, right. Good, 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 good. Right. So if you have taken the advantage of this, then I'm very happy about that one. This is for you all only. Right? So take the advantage. Right. Okay. Can you all hear me now? Again, can you hear me? Right. So, okay, I'm going to wind up the session, students. Let's do the, yes, let's start the second unit and third unit in the next Saturday class. I'm going to post your tutorials this Monday. you will get the tutorials before next Saturday. So let's start the second unit and third unit in the next class. Okay, and we are going to start the paper session also, paper discussion session Wednesday. I'll let you know about that one through a message in the WhatsApp group. Okay, so keep doing your good works, right? Study. So then let's meet on the next Saturday, right? Okay, then until then, have fun. Bye. Good night. Okay. Okay, right.